Basic fuel system requirements. All powered aircraft require fuel on board to operate the engines. A fuel system consisting of storage tanks, pumps, filters, valves, fuel lines, metering devices, and monitoring devices is designed and certified under strict Title 14 of the Code of Federal Regulations, 14 CFR guidelines. Each system must provide an uninterrupted flow of contaminant-free fuel, regardless of the aircraft's attitude. Since fuel load can be a significant portion of the aircraft's weight, a sufficiently strong airframe must be designed. Varying fuel loads and shifts in weight during maneuvers must not negatively affect control of the aircraft in flight. Each Federal Aviation Administration, FAA, certified aircraft is designed and constructed under regulations applicable to that type of aircraft. The certification airworthiness standards are found in 14 CFR as follows. 14 CFR Part 23, Airworthiness Standards. Normal Category Airplanes. 14 CFR Part 25, Airworthiness Standards. Transport Category Airplanes. 14 CFR Part 27, Airworthiness Standards. Normal Category Rotorcraft. 14 CFR Part 29, Airworthiness Standards. Transport Category Rotorcraft. 14 CFR Part 31, Airworthiness Standards. Manned Free Balloons. Additional information is found in 14 CFR Part 33. It addresses airworthiness standards for engines and pertains mainly to engine fuel filter and intake requirements. Title 14 of the CFR, Part 23, Airworthiness Standards, Normal Category Airplanes, Section 23.2430, Fuel Systems, is summarized below. Airworthiness standards specified for air carrier and helicopter certification are similar. Although the technician is rarely involved with designing fuel systems, a review of these criteria gives insight into how an aircraft fuel system operates. Each fuel system must be constructed and arranged to ensure fuel flow at a rate and pressure established for proper engine and auxiliary power unit, APU, functioning under each likely operating condition. This includes any maneuver for which certification is requested, and during which the engine or APU may be in operation. Figure 14:1. Each fuel system must be arranged so that no fuel pump can draw fuel from more than one tank at a time. There must also be a means to prevent the introduction of air into the system. Each fuel system for a turbine engine-powered airplane must meet applicable fuel venting requirements. 14 CFR Part 34 outlines requirements that fall under the jurisdiction of the Environmental Protection Agency, EPA. A turbine engine fuel system must be capable of sustained operation throughout its flow and pressure range, even though the fuel has some water in it. The standard is that the engine continues to run using fuel initially saturated with water at 80 degrees, having 0.75 cubic centimeters, cm, of free water per gallon added to it, and then cooled to the most critical condition for icing likely to be encountered in operation. Fuel system independence. Each fuel system must be designed and arranged to provide independence between multiple fuel storage and supply systems so that failure of any one component in one system will not result in loss of fuel storage or supply of another system. Fuel system. Lightning protection. The fuel system must be designed and arranged to prevent the ignition of the fuel within the system by direct lightning strikes or swept lightning strokes to areas where such occurrences are highly probable, or by corona or streamering at fuel vent outlets. A corona is a luminous discharge that occurs as a result of an electrical potential difference between the aircraft and the surrounding area. Streamering is a branch-like ionized path that occurs in the presence of a direct stroke or under conditions when lightning strikes are imminent. Figure 14:2. Fuel flow. The ability of the fuel system to provide the fuel necessary to ensure each power plant and auxiliary power unit functions properly in all likely operating conditions. It must also prevent hazardous contamination of the fuel supplied to each power plant and auxiliary power unit. The fuel system must provide the flight crew with a means to determine the total usable fuel available and provide uninterrupted supply of that fuel when the system is correctly operated, accounting for likely fuel fluctuations. It should also provide a means to safely remove or isolate the fuel stored in the system from the airplane and be designed to retain fuel under all likely operating conditions and minimize hazards to the occupants during any survivable emergency landing. For Level 4 airplanes, failure due to overload of the landing system must be taken into account. Fuel storage system. Each fuel tank must be able to withstand, without failure, the loads under likely operating conditions. Each tank must be isolated from personnel compartments and protected from hazards due to unintended temperature influences. The fuel storage system must provide fuel for at least 1/2 hour of operation at maximum continuous power or thrust and be capable of jettisoning fuel safely if required for landing. Figure 14-3. Fuel jettisoning systems are also referred to as fuel dump systems. Figure 14-4. A fuel dump system is a system installed in most large aircraft that allows the flight crew to jettison, or dump, fuel to lower the gross weight of the aircraft to its allowable landing weight. Boost pumps in the fuel tanks move the fuel from the tank into a fuel manifold. From the fuel manifold, it flows away from the aircraft through dump chutes in each wing tip. The fuel jettison system must be so designed and constructed that it is free from fire hazards. Aircraft fuel tanks must be designed to prevent significant loss of stored fuel from any vent system due to fuel transfer between fuel storage or supply systems or under likely operating conditions. Fuel storage refilling or recharging system. Each fuel storage refilling or recharging system must be designed to prevent improper refilling or recharging, prevent contamination of the fuel stored during likely operating conditions, and prevent the occurrence of any hazard to the airplane or to persons during refilling or recharging. Types of aviation fuel. Each aircraft engine is designed to burn a certain fuel. Use only the fuel specified by the manufacturer. Mixing fuels is not permitted. There are two basic types of fuel discussed in this section. Reciprocating engine fuel, also known as gasoline or avgas, and turbine engine fuel, also known as jet fuel or kerosene. Reciprocating engine fuel, avgas. Reciprocating engines burn gasoline, also known as avgas. It is specially formulated for use in aircraft engines. Combustion releases energy in the fuel, which is converted into the mechanical motion of the engine. Avgas of any variety is primarily a hydrocarbon compound refined from crude oil by fractional distillation. Aviation gasoline is different from the fuel refined for use in turbine-powered aircraft. Avgas is very volatile and extremely flammable, with a low flash point. Turbine fuel is a kerosene-type fuel with a much higher flash point, so it is less flammable. Aircraft engines must perform throughout a wide range of demanding conditions. They must be lightweight and produce significant power in a wide range of atmospheric and engine operating temperatures. The gasoline used must support uninterrupted combustion throughout this range and must truly burn rather than explode or detonate. This ensures maximum power derivation and minimal engine wear. Over the years, avgas has been available in different formulas. These mostly correlate to how much energy can be produced without the fuel detonating. Larger, high-compression engines require fuel with a greater amount of potential power production without detonation than smaller, low-compression engines. Volatility. One of the most important characteristics of an aircraft fuel is its volatility. Volatility is a term used to describe how readily a substance changes from liquid into a vapor. For reciprocating engines, highly volatile fuel is desired. Liquid gasoline delivered to the engine induction system carburetor, must vaporize in the carburetor to burn in the engine. Fuel with low volatility vaporizes slowly. This can cause hard engine starting, slow warm-up, and poor acceleration. It can also cause uneven fuel distribution to the cylinders and excessive dilution of the oil in the crankcase in engines equipped with oil dilution systems. However, fuel can also be too volatile, causing detonation and vapor lock. Avgas is a blend of numerous hydrocarbon compounds, each with different boiling points and volatility. A straight chain of volatile compounds creates a fuel that vaporizes easily for starting, but also delivers power through the acceleration and power ranges of the engine. Vapor lock. Vapor lock is a condition in which avgas vaporizes in the fuel line or other components between the fuel tank and the carburetor. This typically occurs on warm days on aircraft, with engine-driven fuel pumps that suck fuel from the tanks. Vapor lock can be caused by excessively hot fuel, low pressure, or excessive turbulence of the fuel traveling through the fuel system. In each case, liquid fuel vaporizes prematurely and blocks the flow of liquid fuel to the carburetor. Aircraft gasoline is refined to have a vapor pressure be between 5.5 pounds per square inch, psi, and 7.0 psi at 100 degrees. At this pressure, an aircraft fuel system is designed to deliver liquid fuel to the carburetor when drawn out of the tank by an engine-driven fuel pump. But temperatures in the fuel system can exceed 100 degrees under the engine cowl on a hot day. Fuel may vaporize before it reaches the carburetor, especially if it is drawn up a line under a low pressure, or if it swirls while navigating a sharp bend in the tubing. To make matters worse, when an aircraft climbs rapidly, the pressure on the fuel in the tank decreases while the fuel is still warm. This causes an increase in fuel vaporization that can also lead to vapor lock. Various steps can be taken to prevent vapor lock. The use of boost pumps located in the fuel tank that force pressurized liquid fuel to the engine is most common. Carburetor icing. As fuel vaporizes, it draws energy from its surroundings to change state from a liquid to a vapor. This can be a problem if water is present. When fuel vaporizes in the carburetor, water in the fuel-air mixture can freeze and deposit inside the carburetor and fuel induction system. The fuel discharge nozzle, throttle valve, venturi, or simply the walls of the induction system all can develop ice. As the ice builds, it restricts the fuel airflow and causes loss of engine power. In severe cases, the engine stops running. Figure 14.5. Carburetor icing is most common at ambient temperatures of 30–40 degrees Fahrenheit but can occur at much higher temperatures, especially in humid conditions. Most aircraft are equipped with carburetor heating to help eliminate this threat caused by the high volatility of the fuel and the presence of moisture. Figure 14.6. Aromatic fuels. The aviation gasoline market is a relatively small part of the overall gasoline market. Avgas producers are few. In years past, when this was less the case, considerable quantities of aromatic hydrocarbons were sometimes added to increase the rich mixture performance of avgas. It was used mainly in high-horsepower reciprocating engines, such as military and transport category aircraft. Special hoses and seals were required for use of aromatic fuels. These additives are no longer available. Detonation. Detonation is the rapid, uncontrolled explosion of fuel due to high pressure and temperature in the combustion chamber. The fuel-air charge ignites and explodes before the ignition system spark lights it. Occasionally, detonation occurs when the fuel is ignited via the spark plug, but explodes before it is finished burning. The engine is not designed to withstand the forces caused by detonation. It is made to turn smoothly by having the fuel-air mixture burn in the combustion chamber and propagate directionally across the top of the piston. When it does so, a smooth transfer of the force developed by the burning fuel pushes the piston down. Detonation of fuel instead sends a shock wave of force against the top of the piston, which in turn is transferred through the piston to the piston pin, to the connecting rod, and to the crankshaft. Valve operation is also affected by this shock wave. In short, the explosion of fuel detonating in the combustion chamber transfers the energy contained in the fuel harshly throughout the entire engine, causing damage. Aviation fuels are refined and blended to avoid detonation. Each has an ignition point and burn speed at specific fuel-air mixture ratios that manufacturers rely on to design engines that can operate without detonation. An engine experiencing detonation in the field should be investigated. A pinging or knocking sound is a sign of detonation. This is often more difficult to detect in an aircraft than in an automobile due to propeller tip noise. Detonation causes an increase in cylinder head temperature. If ignored or allowed to continue, detonation can eventually lead to engine failure. Causes of detonation include incorrect fuel, already high engine temperature at high power settings, such as takeoff, pre-ignition of the fuel, extended operations with an extremely lean mixture, and operation at high revolutions per minute, RPM, with low airspeed. Surface ignition and pre-ignition. A sharp deposit or incandescent hotspot in the combustion chamber can cause fuel to ignite before the spark plug lights it. Detonation can cause such an area to form, as can a cracked spark plug insulator or a sharp valve edge. The result could be ignition of the fuel before the piston is at the proper place during its movement toward top dead center of the compression stroke. The extended burn period of the fuel can increase temperatures and pressure in the combustion chamber to the point at which the fuel detonates. The repeated incorrect flame propagation and detonation can cause serious engine damage and eventual engine failure. Figure 14.7. Maintenance personnel should ensure that the correct fuel is being used and that the engine is being operated correctly. Spark plugs and valves should be checked for wear. Signs of deposits and detonation must also be investigated and addressed. Octane and performance number rating. Octane ratings and performance numbers are given to fuels to describe their resistance to detonation. Fuels with high critical pressure and high octane or performance numbers have the greatest resistance. A referencing system is used to rate the fuel. A mixture of two hydrocarbons, isooctane, C8H18, and heptane, C7H16, is used. Various ratios of the two hydrocarbons in a mixture result in proportional anti-detonation properties. The more isooctane there is in the mixture, the higher its resistance is to detonation. When a fuel has the same critical pressure as a reference mixture of these two hydrocarbons, it is said to have an octane rating that is the same as the percentage of the isooctane in this reference mixture. An 80-octane fuel has the same resistance to detonation as an 80% isooctane, 20% heptane mixture. A 90-octane fuel has the same resistance to detonation as a 90% isooctane, 10% heptane mixture. And a 100-octane fuel has the same resistance to detonation as 100% pure isooctane. So by comparing a fuel's tendency to detonate to reference mixtures of isooctane and heptane, octane ratings from 80 to 100 can be established. The highest octane fuel possible with this system of measurement is 100-octane fuel. To increase anti-detonation characteristics of fuel, substances can be added. Tetraethyl lead, TEL, is the most common additive that increases the critical pressure and temperature of a fuel. However, additional additives, such as ethylene dibromide and tricrysyl phosphate, must also be added so that the TEL does not leave solid deposits in the combustion chamber. The amount of TEL added to a fuel can be increased to raise the anti-detonation characteristics from 80 to the 100-octane level and higher. References to octane characteristics above 100% isooctane are made by referencing the anti-detonation properties of the fuel to a mixture of pure isooctane and specific quantities of TL. The specific mixtures of isooctane and TL are assigned arbitrary octane numbers above 100. In addition to increasing the anti-detonation characteristics of a fuel, TEL also lubricates the engine valves. Performance numbers are also used to characterize the anti-detonation characteristics of fuel. A performance number consists of two numbers, e.g. 80-87, 100-130, 115-145, in which higher numbers indicate a higher resistance to detonation. The first number indicates the octane rating of the fuel in a lean fuel-air mixture, and the second number indicates the octane rating of the fuel in a rich mixture. Due to the small size of the worldwide aviation gasoline market, a single 100-octane low-lead fuel, 100 LL, is desired as the only avgas for all aircraft with reciprocating engines. This presents problems in engines originally designed to run on 80-87 fuel. The low-lead 100-octane fuel still contains more lead than the 80-octane fuel. Spark plug fouling has been common, and lower times between overhaul have occurred. Other engines designed for 91-96 fuel or 100-130 fuel operate satisfactorily on 100 LL, which contains 2 milliliters of TL per gallon, enough to lubricate the valves and control detonation. For environmental purposes, avgas with no TEL is sought for the aviation fleet of the future. Fuel identification. Aircraft and engine manufacturers designate approved fuels for each aircraft and engine, consult manufacturer data, and use only those fuels specified therein. The existence of more than one fuel makes it imperative that fuel be positively identified and never introduced into a fuel system that is not designed for it. The use of dyes in fuel helps aviators monitor fuel type. 100 LL avgas is the avgas most readily available and used in the United States. It is dyed blue. Some 100-octane or 100-130 fuel may still be available, but it is dyed green. 80-87 avgas is no longer available. It was dyed red. Many supplemental type certificates have been issued to engine and engine airframe combinations that permit the use of automobile gasoline in engines originally designed for red avgas. A relatively new avgas fuel, 82UL, unleaded, has been introduced for use by this group of relatively low compression engines. It is dyed purple. 115-145 avgas is a fuel designed for large, high-performance reciprocating engines from the World War II era. It is available only by special order from refineries and is also dyed purple in color. The color of fuel may be referred to in older maintenance manuals. All grades of jet fuel are colorless or straw-colored. This distinguishes them from avgas of any kind that contains dye of some color. Should avgas fuel not be of a recognizable color, the cause should be investigated. Some color change may not affect the fuel. Other times, a color change may be a signal that fuels have been mixed or contaminated in some way. Do not release an aircraft for flight with unknown fuel on board. Identifying fuel and ensuring the correct fuel is delivered into storage tanks, fuel trucks, and aircraft fuel tanks is a process aided by labeling. Decals and markings using the same colors as the AV gas colors are used. Delivery trucks and hoses are marked as are aircraft tank fuel caps and fill areas. Jet fuel fill hose nozzles are sized too large to fit into an avgas tank fill opening. Figure 14-8 shows examples of color-coded fuel labeling. Purity. The use of filters in the various stages of transfer and storage of avgas removes most foreign sediment from the fuel. Once in the aircraft fuel tanks, debris should settle into the fuel tank drain sumps to be removed before flight. Filters and strainers in the aircraft fuel system can successfully capture any remaining sediment. The purity of aviation gasoline is compromised most often by water. Water also settles into the sumps given enough time. However, Water is not removed by the aircraft's filters and strainers as easily as solid particles. It can enter the fuel even when the aircraft is parked on the ramp, with the fuel caps in place. Air in the tank vapor space above the liquid fuel contains water vapor. Temperature fluctuations cause the water vapor to condense on the inner surface of the tanks and settle into the liquid fuel. Eventually, this settles to the sump, but some can remain in the fuel when the aircraft is to be flown. Proper procedure for minimizing water entering aircraft fuel is to fill the aircraft fuel tanks immediately after each flight. This minimizes the size of the vapor space above the liquid fuel and the amount of air and associated water vapor present in the tank. When excessive water is drawn into the fuel system, it passes through carburetor jets, where it can interrupt the smooth operation of the engine. If water is entrained or dissolved in the fuel, it cannot be removed by draining the sumps and filter bowls before flight. However, there may be enough water for icing to be a concern. As the aircraft climbs and fuel is drawn out of the tanks, the fuel supply cools. Entrained and dissolved water in the fuel is forced out of solution and becomes free water. If cool enough, ice crystals form rather than liquid water. These can clog filters and disrupt fuel flow to the engines. Both avgas and jet fuel have this type of water impurity issue, leading to icing that must be monitored and treated. Fuel anti-ice additives can be added to the bulk fuel and also directly into the aircraft fuel tank, usually during refueling. These are basically diethylene glycol solutions that work as antifreeze. They dissolve in free water as it comes out of the fuel and lower its freezing point. Figure 14-9. Turbine engine fuels. Aircraft with turbine engines use a type of fuel different from that of reciprocating aircraft engines. Commonly known as jet fuel, turbine engine fuel is designed for use in turbine engines and should never be mixed with aviation gasoline or introduced into the fuel system of a reciprocating aircraft engine fuel system. The characteristics of turbine engine fuels are significantly different from those of avgas. Turbine engine fuels are hydrocarbon compounds of higher viscosity with much lower volatility and higher boiling points than gasoline. In the distillation process from crude oil, the kerosene cut from which jet fuel is made condenses at a higher temperature than the naphtha or gasoline cuts. The hydrocarbon molecules of turbine engine fuels are composed of more carbon than are in avgas. Figure 14-10. Turbine engine fuels sustain a continuous flame inside the engine. They typically have a higher sulfur content than gasoline, and various inhibitors are commonly added to them. Used to control corrosion, oxidation, ice, and microbial and bacterial growth, these additives often are already in the fuel when it arrives at the airport for use. Turbine fuel volatility. The choice of turbine engine fuel reflects consideration of conflicting factors. While it is desirable to use a fuel that is low in volatility to resist vapor lock and evaporation while in the aircraft's fuel tanks, turbine engine aircraft operate in cold environments. Turbine engines must start readily and be able to restart while in flight. Fuel with high volatility makes this easier. Avgas has a relatively low maximum vapor pressure compared to automotive gasoline, only 7 psi. But the vapor pressure of Jet A is only 0.125 psi at standard atmospheric conditions. Jet B, a blend of Jet A and gasoline, has higher volatility with a vapor pressure between 2 and 3 psi. Turbine engine fuel types. 3 basic turbine engine fuel types are available worldwide, although some countries have their own unique fuels. The first is Jet A. It is the most common turbine engine fuel available in the continental United States. Globally, Jet A1 is the most popular. Both Jet A and Jet A1 are fractionally distilled in the kerosene range. They have low volatility and low vapor pressure. Flash points range between 110 degrees and 150 degrees. Jet A freezes at 40 degrees Fahrenheit, and Jet A1 freezes at 52.6 degrees Fahrenheit. Most engine operations manuals permit the use of either Jet A or Jet A1. The third basic type of turbine engine fuel available is Jet B. It is a wide-cut fuel that is basically a blend of kerosene and gasoline. Its volatility and vapor pressure reflect this and fall between Jet A and avgas. Jet B is primarily available in Alaska and Canada due to its low freezing point of approximately 58 degrees Celsius, and its higher volatility yields better cold weather performance. Turbine engine fuel issues. Purity issues related to turbine engine fuels are unique. While avgas experiences similar issues of solid particle contamination and icing concerns, the presence of water and fuel-consuming microbes is more prominent in jet fuel, which has different molecular structure and retains water in two principal ways. Some water is dissolved into the fuel. Other water also is entrained in the fuel, which is more viscous than avgas. The greater presence of water in jet fuel allows microbes to assemble, grow, and live on the fuel. Since turbine engine fuels always contain water, microbial contamination is always a threat. The large tanks of many turbine engine aircraft have numerous areas where water can settle and microbes can flourish. Areas between the fuel tank and any water that may come to rest in the bottom of the tanks is where the microbes thrive. These microorganisms form a biofilm that can clog filters, corrode tank coatings, and degrade the fuel. They can be controlled somewhat with the addition of biocides to the fuel. Figure 14-11. Anti-ice additives are also known to inhibit bacterial growth. Since the microbes are sustained by fuel and water, best practices must be followed to keep the water in fuel to a minimum. Avoid having fuel in a storage tank for a prolonged period of time, on or off the aircraft. Drain sumps and monitor the fuel for settled water. Investigate all incidents of water discovered in the fuel. In addition to water in jet fuel supporting the growth of microorganisms, it also poses a threat of icing. Follow the manufacturer's instructions for fuel handling procedures and fuel system maintenance. Aircraft fuel systems. While each manufacturer designs its own fuel system, the basic fuel system requirements referenced at the beginning of this chapter yield fuel systems of similar design and function in the field. In the following sections are representative examples of various fuel systems in each class of aircraft discussed. Others are similar but not identical. Each aircraft fuel system must store and deliver clean fuel to the engines at a pressure and flow rate able to sustain operations regardless of the operating conditions of the aircraft. Small single-engine aircraft fuel systems. Small single-engine aircraft fuel systems vary depending on factors such as tank location and method of metering fuel to the engine. A high-wing aircraft fuel system can be designed differently from one on a low-wing aircraft. An aircraft engine with a carburetor has a different fuel system than one with fuel injection. Gravity feed systems. High-wing aircraft with a fuel tank in each wing are common. With the tanks above the engine, gravity is used to deliver the fuel. A simple gravity feed fuel system is shown in Figure 14-12. The space above the liquid fuel is vented to maintain atmospheric pressure on the fuel as the tank empties. The two tanks are also vented to each other to ensure equal pressure when both tanks feed the engine. A single screened outlet on each tank feeds lines that connect to either a fuel shutoff valve or multi-position selector valve. The shutoff valve has two positions, fuel on and fuel off. If installed, the selector valve provides four options: fuel shutoff to the engine, fuel feed from the right wing tank only, fuel feed from the left fuel tank only, fuel feed to the engine from both tanks simultaneously. Downstream of the shutoff valve or selector valve, the fuel passes through a main system strainer. This often has a drain function to remove sediment and water. From there, it flows to the carburetor or to the primer pump for engine starting. Having no fuel pump, the gravity feed system is the simplest aircraft fuel system. Pump feed systems. Low and mid-wing single reciprocating engine aircraft cannot utilize gravity feed fuel systems because the fuel tanks are not located above the engine. Instead, one or more pumps are used to move the fuel from the tanks to the engine. A common fuel system of this type is shown in Figure 14 to 13. Each tank has a line from the screened outlet to a selector valve. However, fuel cannot be drawn from both tanks simultaneously. If the fuel is depleted in one tank, the pump would draw air from that tank instead of fuel from the full tank. Since fuel is not drawn from both tanks at the same time, there is no need to connect the tank vent spaces together. From the selector valve, left, right, or off, fuel flows through the main strainer, where it can supply the engine primer. Then it flows downstream to the fuel pumps. Typically, one electric and one engine-driven fuel pump are arranged in parallel. They draw the fuel from the tanks and deliver it to the carburetor. The two pumps provide redundancy. The engine-driven fuel pump acts as the primary pump. The electric pump can supply fuel should the other fail. The electric pump also supplies fuel pressure while starting and is used to prevent vapor lock during flight at high altitude. High-wing aircraft with fuel injection system. Some high-wing, high-performance, single-engine general aviation aircraft are equipped with a fuel system that features fuel injection rather than a carburetor. It combines gravity flow with the use of a fuel pump cess. The Teledyne Continental system is an example. Figure 14 to 14. Note: fuel injection systems spray pressurized fuel into the engine intake or directly into the cylinders. Fuel without any air mixed in is required to provide a measured, continuous spray and smooth engine operation. Fuel pressurized by an engine-driven pump is metered as a function of engine RPM on the Teledyne Continental system. It is first delivered from the fuel tanks by gravity to two smaller accumulator or reservoir tanks. These tanks, one for each wing tank, consolidate the liquid fuel and have a relatively small airspace. They deliver fuel through a three-way selector valve, left, right, or off. The selector valve also acts simultaneously as a diverter of air that has been separated out of the fuel in the engine-driven fuel pump and returned to the valve. It routes the air to the vent space above the fuel in the selected reservoir tank. An electric auxiliary fuel pump draws fuel through the selector valve. It forces the fuel through the strainer, making it available for the primer pump and the engine-driven fuel pump. This pump is typically used for starting and as a backup should the engine-driven pump fail. It is controlled by a switch in the flight deck and does not need to be operating to allow the engine-driven fuel pump access to the fuel. The engine-driven fuel pump intakes the pressurized fuel from the electrically driven pump or from the reservoir tanks if the electric pump is not operating. It supplies a higher than needed volume of fuel under pressure to the fuel control. Excess fuel is returned to the pump, which pumps it through the selector valve into the appropriate reservoir tank. Fuel vapor is also returned to tanks by the pump. The fuel control unit meters the fuel, according to engine RPM and mixture control inputs from the flight deck. The fuel control delivers the fuel to the distribution manifold, which divides it and provides equal, consistent fuel flow for individual fuel injector in each cylinder. Figure 14-15. A fuel flow indicator, tapped off of the distribution manifold, provides feedback in flight deck. It senses fuel pressure, but is displayed on a dial calibrated in gallons per hour. Small multi-engine, reciprocating, aircraft fuel systems. Low-wing twin. The fuel system on a small multi-engine aircraft is more complicated than a single-engine aircraft, but contains many of the same elements. An example system used on a low-wing aircraft is illustrated in Figure 14-16. It features the main fuel tanks in the wing tips and auxiliary tanks in the wing structure. A boost pump is located at the outlet of each main tank. This pressurizes the entire fuel system from the tank to the injectors, eliminating the possibility of vapor lock. An engine can operate with just its boost pump running in the event the engine-driven injection pump fails. Typically, the boost pumps are used to prime and start the engine. 2 selector valves are required on twin-engine aircraft, one for each engine. The right selector valve receives fuel from a main tank on either side of the aircraft and directs it to the right engine. The left selector valve also receives fuel from either main tank and directs it to the left engine. This allows fuel to cross-feed from one side of the aircraft to the opposite engine if desired. The selector valves can also direct fuel from the auxiliary tank to the engine on the same side. Cross-feed of fuel from auxiliary tanks is not possible. From the outlet of the selector valve, fuel flows to the strainer. On some aircraft, the strainer is built into the selector valve unit. From the strainer, fuel flows to the engine-driven fuel pump. The engine-driven fuel pump is an assembly that also contains a vapor separator and a pressure-regulating valve with an adjustment screw. The vapor separator helps eliminate air from the fuel. It returns a small amount of fuel and any vapor present back to the main fuel tank. The pump supplies pressurized fuel to the fuel control. The fuel control, one for each engine, responds to throttle and mixture control settings from the flight deck and supplies the proper amount of fuel to the fuel manifold. The manifold divides the fuel and sends it to an injector in each cylinder. A fuel pressure gauge is placed between the fuel control unit outlet and the manifold to monitor the injector-applied pressure that indicates engine power. High-wing twin. A simplified system on a high-wing twin-engine aircraft that combines gravity feed with an electric fuel pump is illustrated in Figure 14 to 17. Directly downstream of the selector valves are the fuel strainers, and then an electric fuel pump for each engine. This pump draws fuel from the selected tank and sends it under pressure to the inlet side of the fuel injection metering unit. The metering unit for each engine provides the proper flow of fuel to the distribution manifold, which feeds the injectors. Large reciprocating engine aircraft fuel systems. Large multi-engine transport aircraft powered by reciprocating radial engines are no longer produced. However, many are still in operation. They are mostly carbureted and share many features with the light aircraft systems previously discussed. Figure 14 to 18 shows the fuel system of a DC-3. A selector valve for each engine allows an engine-driven pump to pull fuel from the main tank or an auxiliary tank. The fuel passes through a strainer before reaching the pump where it is delivered to the engine. The outlet of the pump can feed either engine through the use of a cross-feed line with valves controlled in the flight deck. A hand-operated wobble pump located upstream of the strainer is used to prime the system for starting. Fuel vapor lines run from the pressure carburetor to the vent space in the main and auxiliary tanks. Fuel pressure gauges are tapped off of the carburetor for power indication. The hand-operated wobble pumps were replaced by electric pumps on later model aircraft. A fuel pressure warning light tapped in downstream of the engine-driven fuel pump alerts the crew should fuel pressure decline. Not all large old aircraft have this fuel system. This is merely an example. Other aircraft share similar features and possess unique features of their own. The same is true for small reciprocating engine aircraft. There are many systems that share features with those described above, but they also differ in some ways. Always consult the manufacturer's data when working on aircraft fuel systems, and follow all instructions for service and repair. The fuel system of an aircraft provides the lifeblood for engine operation, and must be maintained with the highest discretion. Jet transport aircraft fuel systems. Fuel systems on large transport category jet aircraft are complex with some features and components not found in reciprocating engine aircraft fuel systems. They typically contain more redundancy and facilitate numerous options from which the crew can choose while managing the aircraft's fuel load. Features like an onboard APU, single-point pressure refueling, and fuel jettison systems, which are not needed on smaller aircraft, add to the complexity of an airliner fuel system. Jet transport fuel systems can be regarded as a handful of fuel subsystems as follows. 1. Storage. 2. Vent. 3. Distribution. 4. Feed. 5. Indicating. Most transport category aircraft fuel systems are very much alike. Integral fuel tanks are the norm, with much of each wing's structure sealed to enable its use as a fuel tank. Center wing section or fuselage tanks are also common. These may be sealed structure or bladder type. Jet transport aircraft carry tens of thousands of pounds of fuel on board. Figure 1419 shows a diagram of a Boeing 777 fuel tank configuration with tank capacities. There are optional fuel storage configurations available on the same model airliner. For example, airlines expecting to use an aircraft on transoceanic flights may order the aircraft with long-range auxiliary tanks. These additional tanks, usually located in the fuselage section of the aircraft, can alter fuel management logistics in addition to complicating the fuel system. In addition to main and auxiliary fuel tanks, surge tanks may also be found on jet transports. These normally empty tanks, located in the wing structure outboard of the main wing tanks, are used for fuel overflow. A check valve allows the one-way drainage of fuel back into the main tanks. Surge tanks are also used for fuel system venting. Transport category fuel systems require venting, similar to reciprocating engine aircraft fuel systems. A series of vent tubing and channels exists that connects all tanks to vent space in the surge tanks, if present, or vent overboard. Venting must be configured to ensure the fuel is vented regardless of the attitude of the aircraft or the quantity of fuel on board. This sometimes requires the installation of various check valves, float valves, and multiple vent locations in the same tank. Figure 14 to 20 shows the fuel vent system of a Boeing 737. A transport category aircraft fuel distribution subsystem consists of the pressure fueling components, defueling components, transfer system, and fuel jettison or dump system. Single-point pressure fueling at a fueling station accessible by ramp refueling trucks allows all aircraft fuel tanks to be filled with one connection of the fuel hose. Leading and trailing edge wing locations are common for these stations. Figure 14 to 21 shows an airliner fueling station with the fueling rig attached. To fuel with pressure refueling, a hose nozzle is attached at the fueling station, and valves to the tanks required to be filled are opened. These valves are called fueling valves or refueling valves depending upon the manufacturer's preference. Various automatic shutoff systems have been designed to close tank fueling valves before the tanks overfill or are damaged. Gauges on the refueling panel allow refueling personnel to monitor progress. Occasionally, defueling the aircraft is required for an inspection or repair. The same fueling station is used, and the hose from the fuel truck is connected to same receptacle used to fuel the aircraft. To allow fuel to exit the aircraft, a defueling valve is opened. Fuel can either be pumped out of the aircraft, using the boost pumps located in the tanks that need to be emptied, or the pump in the refueling truck can be used to draw the fuel out of the tanks. Control over the operation is maintained by positioning various shutoff and cross-feed valves, as well as the defuel valve, so that fuel travels from the tank to the fueling station and into the truck. The fuel transfer system is a series of plumbing and valves that permits movement of fuel from one tank to another on board the aircraft. In-tank fuel boost pumps move the fuel into a manifold, and by opening the fuel valve, or refueling valve, for the desired tank, the fuel is transferred. Not all jet transports have such fuel transfer capability. Through the use of a fuel feed manifold and cross-feed valves, some aircraft simply allow engines to be run off fuel from any tank as a means for managing fuel location. Figure 1422 shows the fuel system diagram for a DC-10. Dedicated transfer boost pumps move fuel into a transfer manifold. Opening the fuel valve on one of the tanks transfers the fuel into that tank. The transfer manifold and boost pumps are also used to jettison fuel overboard by opening the proper dump valves with a transfer boost pump is operating. Additionally, the transfer system can function to supply the engines if the normal engine fuel feed malfunctions. The fuel feed subsystem is sometimes considered part of the fuel distribution system. It is the heart of the fuel system since it delivers fuel to the engines. Jet transport aircraft supply fuel to the engines via in-tank fuel boost pumps, usually 2 per tank. They pump fuel under pressure through a shut-off valve for each engine. A manifold or connecting tubing typically allows any tank to supply any engine through the use of cross-feed valves. Boost pump bypasses allow fuel flow should a pump fail. The engines are designed to be able to run without any fuel boost pumps operating, but each engine's shut-off valve must be open to allow flow to the engines from the tanks. Most jet transport fuel feed systems, or the engine fuel systems, have some means for heating the fuel, usually through an exchange with hot air or hot oil taken from the engine. Figure 14-23 shows the fuel-cooled oil cooler, FCOC, on a Rolls-Royce RB211 engine, which not only heats the fuel, but also cools the engine oil. Fuel indicating systems on jet transport aircraft monitor a variety of parameters, some not normally found on general aviation aircraft. Business jet aircraft share many of these features. True fuel flow indicators for each engine are used as the primary means for monitoring fuel delivery to the engines. A fuel temperature gauge is common, as are fuel filter bypass warning lights. The temperature sensor is usually located in a main fuel tank. The indicator is located on the instrument panel or is displayed on a multifunction display, MFD. These allow the crew to monitor the fuel temperature during high-altitude flight in extremely frigid conditions. The fuel filters have bypasses that permit fuel flow around the filters if clogged. Indicator lights illuminate in the flight deck when this occurs. Low fuel pressure warning lights are also common on jet transport aircraft. The sensors for these are located in the boost pump outlet line. They give an indication of possible boost pump failure. Fuel quantity gauges are important features on all aircraft. Indications exist for all tanks on a transport category aircraft. Often, these use a capacitance-type fuel quantity indication system and a fuel totalizer, as is discussed later in this chapter. The location of fuel instrumentation varies depending on the type of flight deck displays utilized on the aircraft. Helicopter fuel systems. Helicopter fuel systems vary. They can be simple or complex depending on the aircraft. Always consult the manufacturer's manuals for fuel system description, operation, and maintenance instructions. Typically, a helicopter has only 1 or 2 fuel tanks located near the center of gravity, CG, of the aircraft, which is near the main rotor mast. Thus, the tank, or tanks, are usually located in or near the aft fuselage. Some helicopter fuel tanks are mounted above the engine, allowing for gravity fuel feed. Others use fuel pumps and pressure feed systems. Fundamentally, helicopter fuel systems differ little from those on fixed-wing aircraft. Gravity feed systems have vented fuel tanks with an outlet strainer and shutoff valve. Fuel flows from the tank through a main filter to the carburetor. Figure 14-24. A slightly more complex system for a light turbine-powered helicopter is shown in Figure 14-25. 2 in-tank electric boost pumps send fuel through a shutoff valve rather than a selector valve, since there is only 1 fuel tank. It flows through an airframe filter to an engine filter, and then to the engine-driven fuel pump. The fuel tank is vented and contains an electrically operated sump drain valve. A pressure gauge is used to monitor boost pump output pressure, and differential pressure switches warn of fuel filter restrictions. Fuel quantity is derived through the use of two in-tank fuel probes with transmitters. Larger, heavy, multi-engine transport helicopters have complex fuel systems similar to jet transport fixed-wing aircraft. They may feature multiple fuel tanks, cross-feed systems, and pressure refueling. Fuel system components. To better understand aircraft fuel systems and their operation, the following discussion of various components of aircraft fuel systems is included. Fuel tanks. There are three types of aircraft fuel tanks: rigid removable tanks, bladder tanks, and integral fuel tanks. The type of aircraft, its design and intended use, as well as the age of the aircraft, determine which fuel tank is installed in an aircraft. Most tanks are constructed of non-corrosive material. They are typically made to be vented either through a vent cap or a vent line. Aircraft fuel tanks have a low area called a sump that is designed as a place for contaminants and water to settle. The sump is equipped with a drain valve used to remove the impurities during pre-flight walk-around inspection. Figure 14-26. Most aircraft fuel tanks contain some sort of baffling to subdue the fuel from shifting rapidly during flight maneuvers. Use of a scupper constructed around the fuel fill opening to drain away any spilled fuel is also common. Rigid removable fuel tanks. Many aircraft, especially older ones, utilize an obvious choice for fuel tank construction. A rigid tank is made from various materials, and it is strapped into the airframe structure. The tanks are often riveted or welded together, and can include baffles, as well as the other fuel tank features described above. They typically are made from 3003 or 5052 aluminum alloy or stainless steel, and are riveted and seam welded to prevent leaks. Many early tanks were made of a thin sheet steel coated with a lead-tin alloy called turniplate. The turniplate tanks have folded and soldered seams. Figure 14-27 shows the parts of a typical rigid removable fuel tank. Regardless of the actual construction of removable metal tanks, they must be supported by the airframe and held in place with some sort of padded strap arrangement to resist shifting in flight. The wings are the most popular location for fuel tanks. Figure 14-28 shows a fuel tank bay in a wing root with the tank straps. Some tanks are formed to be part of the leading edge of the wing. These are assembled using electric resistance welding and are sealed with a compound that is poured into the tank and allowed to cure. Many fuselage tanks also exist. Figure 14-29. In all cases, the structural integrity of the airframe does not rely on the tanks being installed, so the tanks are not considered integral. As new materials are tested and used in aircraft, fuel tanks are being constructed out of materials other than aluminum, steel, and stainless steel. Figure 14-30 shows a rigid removable fuel tank from an ultralight category aircraft that is constructed from VPEL R, isophthalic polyester UL, 1316 UL, 1746 resin, and composite. Its seamless, lightweight construction may lead to the use of this type of tank in other aircraft categories in the future. Being able to remove and repair, or replace, a fuel tank can be a great convenience if a leak or malfunction with the tank exists. Repairs to fuel tanks must be done in accordance with manufacturer's specifications. It is especially critical to follow all safety procedures when welding repairs are performed. Fuel vapors must be removed from the tank to prevent explosion. This typically involves washing out the tank with water and detergent, followed by a steam or water flush, as determined by the manufacturer. Once repaired, fuel tanks need to be pressure checked, usually while installed in the airframe, to prevent distortion while under pressure. Bladder fuel tanks. A fuel tank made out of a reinforced flexible material called a bladder tank can be used instead of a rigid tank. A bladder tank contains most of the features and components of a rigid tank, but does not require as large an opening in the aircraft skin to install. The tank, or fuel cell, as it is sometimes called, can be rolled up and put into a specially prepared structural bay or cavity through a small opening, such as an inspection opening. Once inside, it can be unfurled to its full size. Bladder tanks must be attached to the structure with clips or other fastening devices. They should lie smooth and unwrinkled in the bay. It is especially important that no wrinkles exist on the bottom surface, so that fuel contaminants are not blocked from settling into the tank sump. Figure 14 to 31. Bladder fuel tanks are used on aircraft of all sizes. They are strong and have a long life with seams only around installed features, such as the tank vents, sump drain, filler spout, etc. When a bladder tank develops a leak, the technician can patch it following manufacturer's instructions. The cell can also be removed and sent to a fuel tank repair station, familiar with and equipped to perform such repairs. The soft, flexible nature of bladder fuel tanks requires that they remain wet. Should it become necessary to store a bladder tank without fuel in it for an extended period of time, it is common to wipe the inside of the tank with a coating of clean engine oil. Follow the manufacturer's instructions for the dry storage procedures for fuel cells. Integral fuel tanks. On many aircraft, especially transport category and high-performance aircraft, part of the structure of the wings or fuselage is sealed with a fuel-resistant two-part sealant to form a fuel tank. The sealed skin and structural members provide the highest volume of space available with the lowest weight. This type of tank is called an integral fuel tank, since it forms a tank as a unit within the airframe structure. Integral fuel tanks in the otherwise unused space inside the wings are most common. Aircraft with integral fuel tanks in the wings are said to have wet wings. For fuel management purposes, sometimes a wing is sealed into separate tanks and may include a surge tank or an overflow tank, which is normally empty but sealed to hold fuel when needed. When an aircraft maneuvers, the long horizontal nature of an integral wing tank requires baffling to keep the fuel from sloshing. The wing ribs and box beam structural members serve as baffles, and others may be added specifically for that purpose. Baffle check valves are commonly used. These valves allow fuel to move to the low, inboard sections of the tank, but prevent it from moving outboard. They ensure that the fuel boost pumps located in the bottom of the tanks, at the lowest points above the sumps, always have fuel to pump, regardless of aircraft attitude. Figure 1432. Integral fuel tanks must have access panels for inspection and repairs of the tanks and other fuel system components. On large aircraft, technicians physically enter the tank for maintenance. Transport category aircraft often have more than a dozen oval access panels or tank plates on the bottom surface of the wing for this purpose. Figure 1433A. These aluminum panels are each sealed into place with an O-ring and an aluminum gasket for electrostatic bonding. An outer clamp ring is tightened to the inner panel with screws, as shown in Figure 1433B. When entering and performing maintenance on an integral fuel tank, all fuel must be emptied from the tank and strict safety procedures must be followed. Fuel vapors must be purged from the tank and respiratory equipment must be used by the technician. A full-time spotter must be positioned just outside of the tank to assist if needed. Aircraft using integral fuel tanks normally have sophisticated fuel systems that include in-tank boost pumps. There are usually at least 2 pumps in each tank that deliver fuel to the engines under positive pressure. On various aircraft, these in-tank boost pumps are also used to transfer fuel to other tanks, jettison fuel, and defuel the aircraft. Fuel lines and fittings. Aircraft fuel lines can be rigid or flexible, depending on location and application. Rigid lines are often made of aluminum alloy and are connected with Army-Navy (AN) or military standard (MS) fittings. However, in the engine compartment, wheel wells, and other areas subject to damage from debris, abrasion, and heat, stainless steel lines are often used. Flexible fuel hose has a synthetic rubber interior with a reinforcing fiber braid wrap covered by a synthetic exterior. Figure 1434. The hose is approved for fuel, and no other hose should be substituted. Some flexible fuel hoses have a braided stainless steel exterior. Figure 14-35. The diameters of all fuel hoses and lines are determined by the fuel flow requirements of the aircraft fuel system. Flexible hoses are used in areas where vibration exists between components, such as between the engine and the aircraft structure. Sometimes manufacturers wrap either flexible or rigid fuel lines to provide even further protection from abrasion and especially from fire. A fire sleeve cover is held over the line with steel clamps at the end fittings, figure 1436. As mentioned, aircraft fuel line fittings are usually either AN or MS fittings. Both flared and flareless fittings are used. Problems with leaks at fittings can occur. Technicians are cautioned to not over-tighten a leaky fitting. If the proper torque does not stop a leak, depressurize the line, disconnect the fitting, and visually inspect it for a cause. The fitting or line should be replaced if needed. Replace all aircraft fuel lines and fittings with approved replacement parts from the manufacturer. If a line is manufactured in the shop, approved components must be used. Several installation procedures for fuel hoses and rigid fuel lines exist. Hoses should be installed without twisting. The writing printed on the outside of the hose is used as a ley line to monitor fuel hose twist. Separation should be maintained between all fuel hoses and electrical wiring. Never clamp wires to a fuel line. When separation is not possible, always route the fuel line below any wiring. If a fuel leak develops, it does not drip onto the wires. Metal fuel lines and all aircraft fuel system components need to be electrically bonded and grounded to the aircraft structure. This is important because fuel flowing through the fuel system generates static electricity that must have a place to flow to ground rather than build up. Special bonded cushion clamps are used to secure rigid fuel lines in place. They are supported at intervals shown in figure 1437. All fuel lines should be supported so that there is no strain on the fittings. Clamp lines so that fittings are aligned. Never draw two fittings together by threading. They should thread easily, and a wrench should be used only for tightening. Additionally, a straight length of rigid fuel line should not be made between two components or fittings rigidly mounted to the airframe. A small bend is needed to absorb any strain from vibration or expansion and contraction due to temperature changes. Fuel valves. There are many fuel valve uses in aircraft fuel systems. They are used to shut off fuel flow or to route the fuel to a desired location. Other than sump drain valves, light aircraft fuel systems may include only one valve, the selector valve. It incorporates the shutoff and selection features into a single valve. Large aircraft fuel systems have numerous valves. Most simply open and close, and are known by different names related to their location and function in the fuel system, e.g., shutoff valve, transfer valve, crossfeed valve. Fuel valves can be manually operated, solenoid operated, or operated by electric motor. A feature of all aircraft fuel valves is a means for positively identifying the position of the valve at all times. Hand-operated valves accomplish this through the use of detents, into which a spring-loaded pin or similar protrusion locates, when the valve is set in each position. Combined with labels and a directional handle, this makes it easy to identify by feel and by sight that the valve is in the desired position. Figure 14-38. Motor and solenoid-operated valves use position annunciator lights to indicate valve position in addition to the switch position. Flight Management System (FMS) fuel pages also display the position of the fuel valves graphically in diagrams called up on the flat-screen monitors. Figure 1439. Many valves have an exterior position handle, or lever, that indicates valve position. When maintenance personnel directly observe the valve, it can be manually positioned by the technician using this same lever. Figure 14 to 40. Hand-operated valves. There are three basic types of hand-operated valves used in aircraft fuel systems. The cone-type valve and the poppet-type valve are commonly used in light general aviation aircraft as fuel selector valves. Gate valves are used on transport category aircraft as shut-off valves. While many are motor-operated, there are several applications in which gate valves are hand-operated. Cone valves. A cone valve, also called a plug valve, consists of a machined valve, housing into which a rotatable brass or nylon cone is set. The cone is manually rotated by the pilot with an attached handle. Passageways are machined through the cone so that, as it is rotated, fuel can flow from the selected source to the engine. This occurs when the passageway aligns with the desired fuel input port, machined into the housing. Figure 14 to 41 shows a cross-sectional view of a cone valve. The cone can also be rotated to a position so that the passageway does not align with any fuel input port. This is the fuel off position of the valve. Poppet valves. Selector valves are also commonly the poppet type. As the handle is rotated in this valve, a cam on the attached shaft lifts the poppet off the seat of the desired port being selected. At the same time, spring-assisted poppets close off the ports that are not selected. Detents lock the valve into position when the cam pushes a poppet fully off of its seat. There is also a positive detent when the cam engages none of the poppets, which is the off position of the valve. Figure 1442. A similar mechanism is used in some selector valves, but balls are used instead of poppets. Manually operated gate valves. A single selector valve is not used in complex fuel systems of transport category aircraft. Fuel flow is controlled with a series of on-off or shut-off type valves that are plumbed between system components. Hand-operated gate valves can be used, especially as fire control valves, requiring no electrical power to shut off fuel flow when the emergency fire handle is pulled. The valves are typically positioned in the fuel feed line to each engine. Hand-operated gate valves are also featured as ground-operated defuel valves and boost pump isolation valves, which shut off the fuel to the inlet of the boost pump, allowing it to be changed without emptying the tank. Gate valves utilize a sealed gate or blade that slides into the path of the fuel, blocking its flow when closed. Figure 1443 shows a typical hand-operated gate valve. When the handle is rotated, the actuating arm inside the valve moves the gate blade down between seals and into the fuel flow path. A thermal relief bypass valve is incorporated to relieve excess pressure buildup against the closed gate due to temperature increases. Motor-operated valves. The use of electric motors to operate fuel system valves is common on large aircraft due to the remote location from the flight deck of fuel system components. The types of valves used are basically the same as the manually operated valves, but electric motors are used to actuate the units. The two most common electric motor-operated fuel valves are the gate valve and the plug-type valve. The motor-operated gate valve uses a geared, reversible electric motor to turn the actuating arm of the valve that moves the fuel gate into or out of the path of the fuel. As with the manually operated gate valve, the gate or blade is sealed. A manual override lever allows the technician to observe the position of the valve or manually position it. Figure 1444. Less common is the use of a motorized plug-type fuel valve. An electric motor is used to rotate the plug or drum, rather than it being rotated manually. Regardless of the type of valve used, large aircraft fuel system valves either allow fuel to flow or shut off flow. Solenoid-operated valves. An additional way to operate a remotely located fuel valve is through the use of electric solenoids. A poppet-type valve is opened via the magnetic pull developed when an opening solenoid is energized. A spring forces a locking stem into a notch in the stem of the poppet to lock the valve in the open position. Fuel then flows through the opening vacated by the poppet. To close the poppet and shut off fuel flow, a closing solenoid is energized. Its magnetic pull overcomes the force of the locking stem spring and pulls the locking stem out of the notch in the poppet stem. A spring behind the poppet forces it back onto its seat. A characteristic of solenoid-operated fuel valves is that they open and close very quickly. Figure 14 to 45. Fuel pumps. Other than aircraft with gravity-feed fuel systems, all aircraft have at least one fuel pump to deliver clean fuel under pressure to the fuel metering device for each engine. Engine-driven pumps are the primary delivery device. Auxiliary pumps are used on many aircraft as well. Sometimes known as booster pumps or boost pumps, auxiliary pumps are used to provide fuel under positive pressure to the engine-driven pump, and during starting, when the engine-driven pump is not yet up to speed for sufficient fuel delivery. They are also used to back up the engine-driven pump during takeoff and at high altitude to guard against vapor lock. On many large aircraft, boost pumps are used to move fuel from one tank to another. There are many different types of auxiliary fuel pumps in use. Most are electrically operated, but some hand-operated pumps are found on older aircraft. A discussion of the various pump types found in the aviation fleet follows. Hand-operated fuel pumps. Some older reciprocating engine aircraft have been equipped with hand-operated fuel pumps. They are used to back up the engine-driven pump and to transfer fuel from tank to tank. The wobble pumps, as they are known, are double-acting pumps that deliver fuel with each stroke of the pump handle. They are essentially vane-type pumps that have bored passages in the center of the pump, allowing a back-and-forth motion to pump the fuel rather than a full revolution of the vanes, as is common in electrically driven or engine-driven vane-type pumps. Figure 14-46 illustrates the mechanism found in a wobble pump. As the handle is moved down from where it is shown, the vane on the left side of the pump moves up, and the vane on the right side of the pump moves down. As the left vane moves up, it draws fuel into chamber A. Because chambers A and D are connected through the bored center, fuel is also drawn into chamber D. At the same time, the right vane forces fuel out of chamber B, through the bored passage in the center of the pump, into chamber C, and out the fuel outlet through the check valve at the outlet of chamber C. When the handle is moved up again, the left vane moves down, forcing fuel out of chambers A and D because the check valve at the inlet of the A chamber prevents fuel from flowing back through the fuel inlet. The right vane moves up simultaneously and draws fuel into chambers B and C. While simple with little to go wrong, a hand-operated pump requires fuel lines to be run into the flight deck to the pump, creating a potential hazard that can be avoided by the use of an electrically driven pump. Modern light reciprocating engine aircraft usually use electric auxiliary pumps, but they often make use of a simple hand pump for priming the engines during starting. These simple devices are single-acting piston pumps that pull fuel into the pump cylinder when the primer knob is pulled aft. When pushed forward, the fuel is pumped through lines to the engine cylinders. Figure 14-47. Centrifugal boost pumps. The most common type of auxiliary fuel pump used on aircraft, especially large and high-performance aircraft, is the centrifugal pump. It is electric motor-driven, and most frequently is submerged in the fuel tank or located just outside of the bottom of the tank with the inlet of the pump extending into the tank. If the pump is mounted outside the tank, a pump removal valve is typically installed so the pump can be removed without draining the fuel tank. Figure 14 to 48. A centrifugal boost pump is a variable displacement pump. It takes in fuel at the center of an impeller and expels it to the outside as the impeller turns. Figure 14:49. An outlet check valve prevents fuel from flowing back through the pump. A fuel feed line is connected to the pump outlet. A bypass valve may be installed in the fuel feed system to allow the engine-driven pump to pull fuel from the tank if the boost pump is not operating. The centrifugal boost pump is used to supply the engine-driven fuel pump, back up the engine-driven fuel pump, and transfer fuel from tank to tank if the aircraft is so designed. Some centrifugal fuel pumps operate at more than one speed, as selected by the pilot, depending on the phase of aircraft operation. Single-speed fuel pumps are also common. Centrifugal fuel pumps located in fuel tanks ensure positive pressure throughout the fuel system, regardless of temperature, altitude, or flight attitude, thus preventing vapor lock. Submerged pumps have fuel-proof covers for the electric motor, since the motor is in the fuel. Centrifugal pumps mounted on the outside of the tank do not require this, but have some sort of inlet that is located in the fuel. This can be a tube in which a shutoff valve is located, so the pump can be changed without draining the tank. The inlet of both types of centrifugal pump is covered with a screen to prevent the ingestion of foreign matter. Figure 14 to 50. Ejector pumps. Fuel tanks with in-tank fuel pumps, such as centrifugal pumps, are constructed to maintain a fuel supply to the pump inlet at all times. This ensures that the pump does not cavitate and that the pump is cooled by the fuel. The section of the fuel tank dedicated for the pump installation may be partitioned off with baffles that contain check valves, also known as flapper valves. These allow fuel to flow inboard to the pump during maneuvers, but does not allow it to flow outboard. Some aircraft use ejector pumps to help ensure that liquid fuel is always at the inlet of the pump. A relatively small diameter line circulates pump outflow back into the section of the tank where the pump is located. The fuel is directed through a venturi that is part of the ejector. As the fuel rushes through the venturi, low pressure is formed. An inlet, or line that originates outside of the tank pump area, allows fuel to be drawn into the ejector assembly where it is pumped into the fuel pump tank section. Together, with baffle check valves, ejector pumps keep a positive head of fuel at the inlet of the pump. Figure 14:51. Pulsating electric pumps. General aviation aircraft often make use of smaller, less expensive auxiliary fuel pumps. The pulsating electric pump, or plunger-type fuel pump, is common. It is usually used in the same manner as a centrifugal fuel pump on larger aircraft, except it is located downstream of the fuel tank outlets. The pulsating electric fuel pump is plumbed in parallel with the engine-driven pump. During starting, it provides fuel before the engine-driven fuel pump is up to speed, and it can be used during takeoff as a backup. It also can be used at high altitudes to prevent vapor lock. The pulsating electric pump uses a plunger to draw fuel in and push fuel out of the pump. It is powered by a solenoid that alternates between being energized and de-energized, which moves the plunger back and forth in a pulsating motion. Figure 14:52 shows the internal workings of the pump. When switched on, current travels through the solenoid coils, which pull the steel plunger down between the coils. Any fuel in chamber C is forced through the small check valve in the center of the plunger and into chamber D. When positioned between the solenoid, the plunger is far enough away from the magnet that it no longer attracts it, and the pivot allows the contacts to open. This disrupts the current to the solenoid. The calibrated spring shown under the plunger is then strong enough to push the plunger up from between the solenoid coils. As the plunger rises, it pushes fuel in chamber D out the pump outlet port. Also, as the plunger rises, it draws fuel into chamber C and through the check valve into chamber C. As the plunger rises, the magnet is attracted to it, and the upward motion closes the points. This allows current flow to the solenoid coils, and the process begins again with the plunger pulled down between the coils, the magnet releasing, and the points opening. The single-acting pulsating electric fuel pump responds to the pressure of the fuel at its outlet. When fuel is needed, the pump cycles rapidly with little pressure at the pump outlet. As fuel pressure builds, the pump slows because the calibrated spring meets this resistance while attempting to force the piston upwards. A spring in the center of the plunger dampens its motion. A diaphragm between the chamber D fuel and an airspace at the top of the pump dampens the output fuel pulses. Vane-type fuel pumps. Vane-type fuel pumps, engine-driven fuel pumps, are the most common types of fuel pumps found on reciprocating engine aircraft. They are used as both engine-driven primary fuel pumps and as auxiliary or boost pumps. Regardless, the vane-type pump is a constant displacement pump that moves a constant volume of fuel with each revolution of the pump. When used as an auxiliary pump, an electric motor rotates the pump shaft. On engine-driven applications, the vane pump is typically driven by the accessory gearbox. As with all vane pumps, an eccentric rotor is driven inside a cylinder. Slots on the rotor allow vanes to slide in and out and be held against the cylinder wall by a central floating spacer pin. As the vanes rotate with the eccentric rotor, the volume space created by the cylinder wall, the rotor and the vanes increases and then decreases. An inlet port is located where the vanes create an increasing volume space and fuel is drawn into the pump. Further around in the rotation, the space created becomes smaller. An outlet port located there causes fuel to be forced from the cylinder. Figure 14 to 53. The engine-driven fuel pump delivers more fuel than the engine needs to operate. However, the constant volume of a vane pump can be excessive. To regulate flow, most vane pumps have an adjustable pressure relief feature. It uses pressure built up at the outlet of the pump to lift a valve off its seat, which returns excess fuel to the inlet side of the pump. Figure 14 to 54 shows a typical vane-type fuel pump with this adjustable pressure relief function. By setting the relief at a certain pressure above the engine fuel metering device air intake pressure, the correct volume of fuel is delivered. The relief pressure is set via the pressure adjustment screw, which tensions the relief valve spring. During engine starting, or if the vane pump is inoperative, fuel must be able to flow through the pump to the fuel metering device. This is accomplished with the use of a bypass valve inside the pump. A lightly sprung plate under the relief valve overcomes spring pressure whenever the pump's inlet fuel pressure is greater than the outlet fuel press. The plate moves down and fuel can flow through the pump. Figure 14 of 55. Compensated vane-type fuel pumps are used when the vane pump is the engine-driven primary fuel pump. The relief valve setting varies automatically to provide the correct delivery of fuel as the air inlet pressure of the fuel metering device changes due to altitude or turbocharger outlet pressure. A vent chamber above a diaphragm attached to the relief mechanism is connected to the inlet air pressure source. As air pressure varies, the diaphragm assists or resists the relief valve spring pressure, resulting in proper fuel delivery for the condition at the fuel metering device. Figure 1456. Fuel filters. Two main types of fuel cleaning devices are utilized on aircraft. Fuel strainers are usually constructed of relatively coarse wire mesh. They are designed to trap large pieces of debris and prevent their passage through the fuel system. Fuel strainers do not inhibit the flow of water. Fuel filters generally are usually fine mesh. In various applications, They can trap fine sediment that can be only thousands of an inch in diameter, and also help trap water. The technician should be aware that the terms strainer and filter are sometimes used interchangeably. Micronic filters are commonly used on turbine-powered aircraft. This is a type of filter that captures extremely fine particles in the range of 10 to 25 microns. A micron is 1/1000 of a millimeter. Figure 14 to 57. All aircraft fuel systems have filters and strainers to ensure that the fuel delivered to the engine, CS, is free from contaminants. The first of these is encountered at the outlet of the fuel tank. A sump is used to encourage the collection of debris in the lowest part of the tank, which can then be drained off before flight. The actual tank outlet for the fuel is positioned above this sump. Some type of screen is used to trap contaminants attempting to flow out of the tank into the fuel system. Finger screens are common on light aircraft. They effectively increase the area of the fuel tank outlet, allowing a large amount of debris to be trapped while still permitting fuel to flow. Figure 14 to 58 illustrates finger screens that are screwed into a fitting welded in the tank outlet. Fuel tank outlet screens on aircraft with more complex fuel systems are similarly designed. When in-tank boost pumps are used, the tank outlet strainer is located at the inlet to the boost pump, as was shown in Figure 1450. The screen's large area allows debris capture while still permitting sufficient fuel flow for operation. Regularly scheduled inspection and cleaning of these strainers are required. An additional main strainer for the aircraft fuel system is required between the fuel tank outlet and the fuel metering device in a carburetor or fuel injection system. It is normally located between the fuel tank and the engine-driven fuel pump at the low point in the fuel system, and is equipped with a drain for pre-flight sampling and draining. On light aircraft, the main strainer may be in the form of a gascolator. A gascolator is a fuel strainer, or filter, that also incorporates a sediment collection bowl. The bowl is traditionally glass to allow quick visual checks for contaminants. However, many gascolators also have opaque bowls. A gascolator has a drain, or the bowl can be removed to inspect and discard trapped debris and water. Figure 1459. The main fuel strainer is often mounted at a low point on the engine firewall. The drain is accessible through an easy-access panel, or it simply extends through the bottom engine cowling. As with most filters or strainers, fuel is allowed to enter the unit, but must travel up through the filtering element to exit. Water, which is heavier than fuel, becomes trapped and collects in the bottom of the bowl. Other debris too large to pass through the element also settles in the strainer bowl. Higher performance light aircraft may have a main filter, strainer. Figure 1460. On twin-engine aircraft, there is a main strainer for each engine. As with single-engine aircraft, a strainer is often mounted low on the engine firewall in each nacelle. Other larger fuel filters have double screen construction. A cylindrical structural screen is wrapped with a fine mesh material through which inlet fuel must pass. Inside the cylinder is an additional cone-shaped screen. Fuel must pass up through the cone to get to the filter outlet. The mesh used in this filter assembly prevents water and particles from exiting the filter bowl. The contaminants collect at the bottom, to be drained off through a drain valve. Figure 14-61. Turbine engine fuel control units are extremely close tolerance devices. It is imperative that fuel delivered to them is clean and contaminant-free. The use of micronic filters makes this possible. The changeable cellulose filter mesh type, shown in Figure 1462, can block particles 10 out of 200 microns in size and absorbs water if it is present. The small size of the mesh raises the possibility of the filter being blocked by debris or water. Therefore, a relief valve is included in the filter assembly that bypasses fuel through the unit should pressure build up from blockage. Fuel filters are often used between the engine-driven fuel pump and the fuel metering device on reciprocating, as well as turbine engine aircraft. While these are technically part of the engine fuel system, A common type used on turbine engines is discussed here. It is also a micronic filter. It uses finely meshed discs or wafers stacked on a central core. These filters are able to withstand the higher pressure found in the engine fuel system downstream of the engine-driven pump. Figure 14-63. Indication of a filter blockage may also appear in the flight deck through the use of a bypass-activated switch or a pressure differential switch. A high fuel differential pressure indicates a blockage to the fuel filter. The bypass valve physically activates a switch that closes the circuit to the annunciator in the first type. The differential pressure type indicator compares the input pressure of the fuel filter to the output pressure. A circuit is completed when a preset difference occurs. Thus, an indicator is illuminated should a blockage cause the bypass to open or the inlet and outlet pressures to vary significantly. Fuel temperature can also be monitored for the possibility of a blockage caused by frozen water. Fuel heaters and ice prevention. Turbine-powered aircraft operate at high altitude where the temperature is very low. As the fuel in the fuel tanks cools, water in the fuel condenses and freezes. It may form ice crystals in the tank or, as the fuel-water solution slows and contacts the cool filter element on its way through fuel filter to the engines. The formation of ice on the filter element blocks the flow of fuel through the filter. A valve in the filter unit bypasses unfiltered fuel when this occurs. Fuel heaters are used to warm the fuel so that ice does not form. These heat exchanger units also heat the fuel sufficiently to melt any ice that has already formed. The most common types of fuel heaters are air fuel heaters and oil fuel heaters. An air fuel heater uses warm compressor bleed air to heat the fuel. An oil fuel exchanger heats the fuel with hot engine oil. This latter type is often referred to as a fuel-cooled oil cooler, FCOC. Figure 14-23. Fuel heaters often operate intermittently as needed. A switch in the flight deck can direct the hot air or oil through the unit or block it. The flight crew uses the information supplied by the filter bypass, indicating lights and fuel temperature gauge, Figure 1464, to know when to heat the fuel. Fuel heaters can also be automatic. A built-in thermostatic device opens or closes a valve that permits the hot air or hot oil to flow into the unit to warm the fuel. Figure 1465. Some aircraft have a hydraulic fluid cooler in one of the aircraft fuel tanks. The fluid helps warm the fuel as it cools in this type of full-time heat exchanger. Fuel system indicators. Aircraft fuel systems utilize various indicators. All systems are required to have some sort of fuel quantity indicator. Fuel flow, pressure, and temperature are monitored on many aircraft. Valve position indicators and various warning lights and annunciations are also used. Fuel quantity indicating systems. All aircraft fuel systems must have some form of fuel quantity indicator. These devices vary widely depending on the complexity of the fuel system and the aircraft on which they are installed. Simple indicators requiring no electrical power were the earliest type of quantity indicators and are still in use today. The use of these direct reading indicators is possible only on light aircraft in which the fuel tanks are in close proximity to the flight deck. Other light aircraft and larger aircraft require electric indicators or electronic capacitance type indicators. A sight glass is a clear glass or plastic tube open to the fuel tank that fills with fuel to the same level as the fuel in the tank. It can be calibrated in gallons or fractions of a full tank that can be read by the pilot. Another type of sight gauge makes use of a float with an indicating rod attached to it. As the float moves up and down with the fuel level in the tank, the portion of the rod that extends through the fuel cap indicates the quantity of fuel in the tank. Figure 14-66. These two mechanisms are combined in yet another simple fuel quantity indicator in which the float is attached to a rod that moves up or down in a calibrated cylinder. Figure 1467. More sophisticated mechanical fuel quantity gauges are common. A float that follows the fuel level remains the primary sensing element, but a mechanical linkage is connected to move a pointer across the dial face of an instrument. This can be done with a crank and pinion arrangement that drives the pointer with gears, or with a magnetic coupling to the pointer. Figure 14-68. Electric fuel quantity indicators are more common than mechanical indicators in modern aircraft. Most of these units operate with direct current, DC, and use variable resistance in a circuit to drive a ratiometer-type indicator. The movement of a float in the tank moves a connecting arm to the wiper on a variable resistor in the tank unit. This resistor is wired in series with one of the coils of the ratiometer-type fuel gauge in the instrument panel. Changes to the current flowing through the tank unit resistor change the current flowing through one of the coils in the indicator. This alters the magnetic field in which the indicating pointer pivots. The calibrated dial indicates the corresponding fuel quantity. Figure 1469. Digital indicators are available that work with the same variable resistance signal from the tank unit. They convert the variable resistance into a digital display in the flight deck instrument head. Figure 14-70. Fully digital instrumentation systems, such as those found in a glass flight deck aircraft, convert the variable resistance into a digital signal to be processed in a computer and displayed on a flat screen panel. Large and high-performance aircraft typically utilize electronic fuel quantity systems. This is also known as a capacitance-type fuel quantity indicating system. These more costly systems have the advantage of having no moving parts in the tank sending units. Variable capacitance transmitters are installed in the fuel tanks extending from the top to the bottom of each tank in the usable fuel. Several of these tank units, or fuel probes as they are sometimes called, may be installed in a large tank. Figure 14-71. They are wired in parallel. As the level of the fuel changes, the capacitance of each unit changes. The capacitance transmitted by all of the probes in a tank is totaled and compared in a bridge circuit by a microchip computer in the tank's digital fuel quantity indicator in the flight deck. As the aircraft maneuvers, some probes are in more fuel than others due to the attitude of the aircraft. The indication remains steady because the total capacitance transmitted by all of the probes remains the same. A trimmer is used to match the capacitance output with the pre-calibrated quantity indicator. A capacitor is a device that stores electricity. The amount it can store depends on three factors: the area of its plates, the distance between the plates, and the dielectric constant of the material separating the plates. A fuel tank unit contains two concentric plates that are a fixed distance apart. Therefore, the capacitance of a unit can change if the dielectric constant of the material separating the plates varies. The units are open at the top and bottom, so they can assume the same level of fuel as is in the tanks. Therefore, the material between the plates is either fuel, if the tank is full, air, if the tank is empty, or some ratio of fuel and air depending on how much fuel remains in the tank. Figure 14-72 shows a simplified illustration of this construction. The bridge circuit that measures the capacitance of the tank units uses a reference capacitor for comparison. When voltage is induced into the bridge, the capacitive reactance of the tank probes and the reference capacitor can be equal or different. The magnitude of the difference is translated into an indication of the fuel quantity in the tank, calibrated in pounds. Some European aircraft display this in kilograms, kg. Figure 14-73 represents the nature of this comparison bridge circuit. The use of tank unit capacitors, a reference capacitor, and a microchip bridge circuit in the fuel quantity indicators is complicated by the fact that temperature affects the dielectric constant of the fuel. A compensator unit, mounted low in the tank so it is always covered with fuel, is wired into the bridge circuit. It modifies current flow to reflect temperature variations of the fuel, which affect fuel density and thus capacitance of the tank units. Figure 14 to 74. An amplifier is also needed in older systems. The amplitude of the electric signals must be increased to move the servo motor in the analog indicator. Additionally, the dielectric constant of different turbine engine fuels approved for a particular aircraft may also vary. Calibration is required to overcome this. A fuel totalizer is part of the capacitance-type fuel quantity indication system. It is used to add the tank quantities from all indicators. This total aircraft fuel quantity can be used by the crew and by flight management computers for calculating optimum airspeed and engine performance limits for climb, cruise, descent, etc. Capacitance-type fuel quantity system test units are available for troubleshooting and ensuring proper functioning and calibration of the indicating system components. Many aircraft with capacitance-type fuel indicating systems also use a mechanical indication system to cross-check fuel quantity indications and to ascertain the amount of fuel on board the aircraft when electrical power is not available. A handful of fuel measuring sticks, or drip sticks, are mounted throughout each tank. When pushed and rotated, the drip stick can be lowered until fuel begins to exit the hole on the bottom of each stick. This is the point at which the top of the stick is equal to the height of the fuel. The sticks have a calibrated scale on them. By adding the indications of all of the drip sticks and converting to pounds or gallons via a chart supplied by the manufacturer, the quantity of the fuel in the tank can be ascertained. Figure 1475. Fuel flow meters. A fuel flow meter indicates an engine's fuel use in real time. This can be useful to the pilot for ascertaining engine performance and for flight planning calculations. The types of fuel flow meter used on an aircraft depends primarily on the power plant being used and the associated fuel system. Measuring fuel flow accurately is complicated by the fact that the fuel mass changes with temperature or with the type of fuel used in turbine engines. In light aircraft with reciprocating engines, systems have been devised to measure fuel volume. The actual mass of fuel flowing to the engine is based on an assumption of the average weight of the fuel per unit volume. The simplest fuel flow sensing device is used in conjunction with fuel injection systems installed on horizontally opposed reciprocating engines. A pressure gauge is used, but it is calibrated in gallons per hour or pounds per hour. The amount of fuel that is flowing through the fuel injectors has a direct relationship to the pressure drop across the fuel injector orifices. Therefore, monitoring fuel pressure at the injectors closely approximates fuel flow and provides useful flow information for mixture control and flight planning. There is a major limitation to the use of fuel pressure as a flow indicator. Should an injector become clogged, fuel flow is reduced. However, the pressure gauge indicates a higher fuel pressure and greater fuel flow due to the restriction. Operators must be aware of this potential condition and check the flow meter against EGT to determine the nature of the elevated indication. Figure 14-76. Large reciprocating engine fuel systems may use a vane-type fuel flow meter that measures the volume of the fuel consumed by the engine. The fuel flow unit is typically located between the engine-driven fuel pump and the carburetor. The entire volume of fuel delivered to the engine is made to pass through the flow meter. Inside, the fuel pushes against the vane, which counters the force of the fuel flow with a calibrated spring. The vane shaft rotates varying degrees matching the fuel flow rate through the unit. An autosyn transmitter deflects the pointer on the flight deck fuel flow gauge the same amount as the vane deflects. The dial face of the indicator is calibrated in gallons per hour or pounds per hour based on an average weight of fuel. Since fuel fed to the engine must pass through the flow meter unit, a relief valve is incorporated to bypass the fuel around the vane should it malfunction and restrict normal fuel flow. The vane chamber is eccentric. As more fuel pushes against the vane, it rotates further around in the chamber. The volume of the chamber gradually increases to permit the greater flow of fuel without restriction or pressure flight deck. The mass flow indicator takes advantage of the buildup. Figure 1477. Turbine engine aircraft experience the greatest range of fuel density from temperature variation and fuel composition. An elaborate fuel flow device is used on these aircraft. It measures fuel mass for accurate fuel flow indication in the flight deck. The mass flow indicator takes advantage of the direct relationship between fuel mass and viscosity. Fuel is swirled by a cylindrical impeller that rotates at a fixed speed. The outflow deflects a turbine just downstream of the impeller. The turbine is held with calibrated springs. Since the impeller motor swirls the fuel at a fixed rate, any variation of the turbine deflection is caused by the volume and viscosity of the fuel. The viscosity component represents the mass of the fuel. Figure 14-78. An alternating current, AC synchro system, is part of the mass fuel flow meter. It is used to position a pointer against the flight deck indicator scale, calibrated in pounds per hour. With accurate fuel flow knowledge, numerous calculations can be performed to aid the pilot's situational awareness and flight planning. Most high-performance aircraft have a fuel totalizer that electronically calculates and displays information, such as total fuel used, total fuel remaining on board the aircraft, total range and flight time remaining at the present airspeed, rate of fuel consumption, etc. On light aircraft, it is common to replace the original analog fuel indicators with electronic gauges containing similar capabilities and built-in logic. Some of these fuel computers, as they are called, integrate global positioning satellite, GPS, location information. Figure 14-79. Aircraft with fully digital flight decks process fuel flow data in computers and display a wide array of fuel flow-related information on demand. Relatively new types of fuel flow sensors, charge transmitters, are available in new aircraft and for retrofit to older aircraft. One type of device found in home-built and experimental aircraft uses a turbine that rotates in the fuel flow. The higher the flow rate is, the faster the turbine rotates. A Hall effect transducer is used to convert the speed of the turbine to an electrical signal to be used by an advanced fuel gauge, similar to a fuel computer, to produce a variety of calculated readouts and warnings. The turbine in this unit is in line with the fuel flow, but is fail-safe to allow adequate fuel flow without interruption should the unit malfunction. Figure 14-80. Another fuel flow sensor used primarily on light aircraft also detects the spinning velocity of a turbine in the fuel path. It too has a fail-safe design should the turbine malfunction. In this unit, notches in the rotor interrupt an infrared light beam between an LED and phototransistor that creates a signal proportional to the amount fuel flow. Figure 1481. This type of sensor may be coupled with an electronic indicator. Increasing use of microprocessors in computers on aircraft enable the integration of fuel temperature and other compensating factors to produce highly accurate fuel flow information. Fuel flow sensing with digital output facilitates this with a high degree of reliability. Thermal dispersion technology provides flow sensing with no moving parts and digital output signals. The sensor consists of two resistance temperature detectors, RTDs. One is a reference RTD that measures the temperature of the fuel. The other is the active RTD. It is heated by an adjacent element to a temperature higher than the fuel. As the fuel flows, the active element cools proportionally to the fuel flow. The temperature difference between the two RTDs is highest at no flow. The RTDs are connected to an electronic assembly that supplies power to the heater and uses sensing circuitry and a microprocessor to control a constant temperature difference between the heated and unheated RTDs. The electrical current to the heater is proportional to the mass flow of the fuel. As mentioned, the reference RTD is used as a temperature sensor to provide a temperature output and allow for temperature compensation of the flow measurement. Figure 1482. Fuel temperature gauges. As previously mentioned, monitoring fuel temperature can inform the pilot when fuel temperature approaches that which could cause ice to form in the fuel system, especially at the fuel filter. Many large and high-performance turbine aircraft use a resistance-type electric fuel temperature sender in a main fuel tank for this purpose. It can display on a traditional ratiometer gauge, figure 14-65, or can be input into a computer for processing and digital display. A low fuel temperature can be corrected with the use of a fuel heater if the aircraft is so equipped. Also, as mentioned, fuel temperature can be integrated into fuel flow processing calculations. Viscosity differences at varying fuel temperatures that affect fuel flow sensing accuracy can be corrected via microprocessors and computers. Fuel pressure gauges. Monitoring fuel pressure can give the pilot early warning of a fuel system-related malfunction. Verification that the fuel system is delivering fuel to the fuel metering device can be critical. Simple light reciprocating engine aircraft typically utilize a direct reading Borden tube pressure gauge. It is connected into the fuel inlet of the fuel metering device with a line extending to the back of the gauge in the flight deck instrument panel. A more complex aircraft may have a sensor with a transducer located at the fuel inlet to the metering device that sends electrical signals to a flight deck gauge. Figure 1483. In aircraft equipped with an auxiliary pump for starting and to back up the engine-driven pump, the fuel pressure gauge indicates the auxiliary pump pressure until the engine is started. When the auxiliary pump is switched off, the gauge indicates the pressure developed by the engine-driven pump. More complex and larger reciprocating engine aircraft may use a differential fuel pressure gauge. It compares fuel inlet pressure to the air inlet pressure at the fuel metering device. A bellows-type pressure gauge is normally used. Figure 1484. Modern aircraft may use a variety of sensors, including solid-state types, and those with digital output signals or signals that are converted to digital output. These can be processed in the instrument gauge microprocessor, if so equipped, or in a computer and sent to the display unit. Figure 1485. Pressure warning signal. On aircraft of any size, visual and audible warning devices are used in conjunction with gauge indications to draw the pilot's attention to certain conditions. Fuel pressure is an important parameter that merits the use of a warning signal when it falls outside of the normal operating range. Low fuel pressure warning lights can be illuminated through the use of simple pressure sensing switches. Figure 1486. The contacts of the switch will close when fuel pressure against the diaphragm is insufficient to hold them open. This allows current to flow to the annunciator or warning light in the flight deck. Most turbine-powered aircraft utilize a low-pressure warning switch at the outlet of each fuel boost pump. The annunciator for each is typically positioned adjacent to the boost pump on-off switch on the fuel panel in the flight deck. Figure 1487. Valve in transit indicator lights. Aircraft with multiple fuel tanks use valves and pumps to move fuel and to have it flow to desired locations, such as the engines, a certain tank, or overboard during fuel jettison. The functioning of the valves in the fuel system is critical. Some aircraft indicate to the crew when the valve is opening or closing with the use of valve-in-transit lights. Contacts in the valve control the lights that go out when the valve is fully open or when it is fully closed. Alternately, annunciator lights that show the valve position as open or closed are also used. Valve in transit and valve position indicators, or lights, are located on the fuel panel in the flight deck adjacent to the valve on-off switches. Figure 1488. Sometimes the switch mechanism has the annunciator light built into it. Digital display systems graphically depict valve positions on screen. Fuel system repair. The integrity of an aircraft fuel system is critical and should not be compromised. Any evidence of malfunction or leak should be addressed before the aircraft is released for flight. The danger of fire, explosion, or fuel starvation in flight makes it imperative that fuel system irregularities be given top priority. Each manufacturer's maintenance and operation instructions must be used to guide the technician in maintaining the fuel system in airworthy condition. Follow the manufacturer's instructions at all times. Component manufacturers and STC holder instructions should be used when applicable. Some general instructions for fuel system maintenance and repair are given in the following sections. Troubleshooting the fuel system. Knowledge of the fuel system and how it operates is essential when troubleshooting. Manufacturers produce diagrams and descriptions in their maintenance manuals to aid the technician. Study these for insight. Many manuals have troubleshooting charts or flow diagrams that can be followed. As with all troubleshooting, a logical sequence of steps to narrow the problem to a specific component or location should be followed. Defects within the system can often be located by tracing the fuel flow from the tank through the system to the engine. Each component must be functioning as designed, and the cause of the defect symptom must be ruled out sequentially. Location of leaks and defects. Close visual inspection is required whenever a leak or defect is suspected in a fuel system. Leaks can often be traced to the connection point of two fuel lines or a fuel line and a component. Occasionally, the component itself may have an internal leak. Fuel leaks also occur in fuel tanks and are discussed below. Leaking fuel produces a mark where it travels. It can also cause a stronger than normal odor. Gasoline may collect enough of its dye for it to be visible, or an area clean of dirt may form. Jet fuel is difficult to detect at first, but it has a slow evaporation rate. Dirt and dust eventually settle into it, which makes it more visible. When fuel leaks into an area where the vapors can collect, the leak must be repaired before flight due to the potential for fire or explosion. Repair could be deferred for external leaks that are not in danger of being ignited. However, the source of the leak should be determined and monitored to ensure it does not become worse. Follow the aircraft manufacturer's instructions on the repair of fuel leaks and the requirements that need to be met for airworthiness. Detailed visual inspection can often reveal a defect. Fuel leak classification. 4 basic classifications are used to describe aircraft fuel leaks: stain, seep, heavy seep, and running leak. Figure 14-89. In 30 minutes, the surface area of the collected fuel from a leak is a certain size. This is used as the classification standard. When the area is less than 3 or 4 inch in diameter, the leak is said to be a stain. From 3/4 to 1/12 inches in diameter, the leak is classified as a seep. Heavy seeps form an area from 1/12 inches to 4 inches in diameter. Running leaks pool and actually drip from the aircraft. They may follow the contour of the aircraft for a long distance. Replacement of gaskets, seals, and packings. A leak can often be repaired by replacing a gasket or seal. When this occurs, or a component is replaced or reassembled after a maintenance operation, a new gasket, seal, or packing must be installed. Do not use the old ones. Always be sure to use the correct replacement as identified by part number. Also, most gaskets, seals, and packings have a limited shelf life. They should be used only if they are within the service life stamped on the package. Remove the entire old gasket completely and clean all mating surfaces. Clean surfaces and grooves allow a tight seal. Inspect new gaskets and seals for any flaws. Follow the manufacturer's instructions for replacement, including cleaning procedures and any sealing compound that you may need to apply during replacement. Torque assembly bolts evenly so as to provide even pressure and prevent pinching. Fuel tank repair. Whether rigid removable, bladder type, or integral, all fuel tanks have the potential to develop leaks. Repair a tank according to the manufacturer's instructions. Some general notes for repair of each tank type follow. At the time a tank is repaired, a thorough inspection should be made. Corrosion, such as that caused by water and microbes, should be identified and treated at this time, even if it is not the cause of the leak. Rigid removable fuel tanks can be riveted, welded, or soldered together. A leak can develop at any of these types of seams, or can be elsewhere on the tank. Generally, the repair must match the construction and technique. Some metal fuel tanks experiencing minor seepage can be repaired with a sloshing procedure. An approved sloshing compound is poured into the tank, and the tank is moved so that the compound coats the entire inner surface area of the tank. Any excess compound is then poured out, and the compound in the tank is allowed to cure for a specified amount of time. Minor gaps in the seams of the tank and repairs are filled in this manner. The compound is fuel-resistant once dry. Check with the aircraft manufacturer to ensure that sloshing is an airworthy repair for the aircraft fuel tank in question. Welded tanks. Welded tank repairs are usually done by welding. These tanks can be constructed from steel or weldable aluminum, such as 3003S or 5052SO. The tank is removed from the aircraft for the repair. It must be treated to remove any fuel vapors that remain in the tank before it is welded. This is critical to avoid serious injury from explosion should the fuel vapor ignite. The manufacturer usually gives a procedure for doing this. Some common methods for purging the tank include steam cleaning, hot water purging, and inert gas purging. Most procedures involve running the steam, water, or gas through the tank for a stated period of time. Adapters may need to be fashioned or purchased for the fill port to enable proper cleaning. Follow the manufacturer's procedure for the proper time to keep the cleaning medium in the tank, and for prepping the tank for welding in general. After a seam or a damaged area is welded, you must clean the tank of any flux or debris that may have fallen into the tank. Water rinsing and acid solutions are commonly used. A leak check to ensure the repair is sound follows a welded repair. This can be done by pressurizing the tank with a specified amount of air pressure and using a soapy solution on all seams and the repaired area. Bubbles form should air escape. The amount of air pressure used for a leak check is very low. 1/2 to 3.5 psi is common. Use an accurate regulator and pressure gauge to prevent overpressurization that could deform or otherwise damage the tank. Tanks ordinarily supported by aircraft structure when installed should be similarly supported or reinstalled in the airframe before pressurization. Figure 14 to 90 shows an aircraft fuel tank being welded and the repaired tank installed in the frame of an antique aircraft. Riveted tanks. Riveted tanks are often repaired by riveting. The seams and rivets are coated with a fuel-resistant compound when assembled to create a leak-free container. This practice is followed during a patch repair or when repairing a seam, which may require replacing the rivets in the seam. Some minor leak repairs may only require the application of addition compound. Follow manufacturer's instructions. The compound used may be heat-sensitive and require inert gas purging to prevent degradation from hot water or steam purging. Again, follow all manufacturer guidance to ensure a safe, airworthy repair. Soldered tanks. Turniplate aircraft fuel tanks that are assembled by soldering are also repaired by soldering. All patches have a minimum amount that must overlap the damaged area. Flux used in soldering must be removed from the tank after the repair, with techniques similar to that used on a welded tank. Follow manufacturer's instructions. Bladder tanks. Bladder fuel tanks that develop leaks can also be repaired. Most commonly, they are patched using patch material, adhesive, and methods approved by the manufacturer. As with soldered tanks, the patch has a required overlap of the damaged area. Damage that penetrates completely through the bladder is repaired with an external as well as internal patch. Synthetic bladder tanks have a limited service life. At some point, they seep fuel beyond acceptable limits and need to be replaced. Bladder tanks are usually required to remain wetted with fuel at all times to prevent drying and cracking of the bladder material. Storage of bladder tanks without fuel can be accomplished by coating the tanks with a substance to prevent drying, such as clean engine oil that can be flushed from the tank when ready to return to service. Follow all manufacturers' instructions for the care and repair of these common tanks. It is important to ensure that bladder tanks are correctly secured in place with the proper fasteners when reinstalling them in the aircraft after a repair. Integral tanks. Occasionally, an integral tank develops a leak at an access panel. This can often be repaired by transferring fuel to another tank, so the panel can be removed and the seal replaced. Use of the proper sealing compound and bolt torque are required. Other integral fuel tank leaks can be more challenging and time-consuming to repair. They occur when the sealant used to seal the tank seams loses its integrity. To repair, fuel needs to be transferred or defueled out of the tank. You must enter large tanks on transport category aircraft. Preparing the tank for safe entry requires a series of steps outlined by the aircraft manufacturer. These include drying the tank and venting it of dangerous vapors. The tank is then tested with a combustible gas indicator to be certain it can be entered safely. Clothing that does not cause static electricity and a respirator is worn. An observer is stationed outside of the tank to assist the technician in the tank. Figure 1491. A continuous flow of ventilating air is made to flow through the tank. A checklist for fuel tank preparation for entry taken from a transport category maintenance manual is shown in Figure 14-92. The details of the procedures are also given in the manual. Once the location of the leak is determined, the tank sealant is removed and new sealant is applied. Remove old sealant with a non-metallic scraper. Aluminum wool can be used to remove the final traces of the sealant. After cleaning the area with the recommended solvent, apply new sealant as instructed by the manufacturer. Observe cure time and leak checks as recommended before refilling the tank. Fire safety, fuel vapor, air, and a source of ignition are the requirements for a fuel fire. Whenever working with fuel or a fuel system component, the technician must be vigilant to prevent these elements from coming together to cause a fire or explosion. A source of ignition is often the most controllable. In addition to removing all sources of ignition from the work area, care must be exercised to guard against static electricity. Static electricity can easily ignite fuel vapor, and its potential for igniting fuel vapor may not be as obvious as a flame or an operating electrical device. The action of fuel flowing through a fuel line can cause a static buildup, as can many other situations in which one object moves past another. Always assess the work area and take steps to remove any potential static electricity ignition sources. Avgas is especially volatile. It vaporizes quickly due to its high vapor pressure and can be ignited very easily. Turbine engine fuel is less volatile, but still possesses enormous capacity to ignite. This is especially true if atomized, such as when escaping out of a pressurized fuel hose or in a hot engine compartment on a warm day. Treat all fuels as potential fire hazards in all situations. As was discussed, empty fuel tanks have an extreme potential for ignition or explosion. Although the liquid fuel has been removed, ignitable fuel vapor can remain for a long period of time. Purging the vapor out of any empty fuel tank is an absolute necessity before any repair is initiated. A fire extinguisher should be on hand during fuel system maintenance or whenever fuel is being handled. A fuel fire can be put out with a typical carbon dioxide, CO2 fire extinguisher. Aim the extinguisher nozzle at the base of the flame and spray in a sweeping motion to have the agent fall over the flames to displace the oxygen and smother the fire. Dry chemical fire extinguishers rated for fuel can also be used. These leave behind a residue that requires cleanup that can be extensive and expensive. Do not use a water-type extinguisher. Fuel is lighter than water and could be spread without being extinguished. Additional precautions used to prevent fire are discussed below in the fueling-defueling section of this chapter. Fuel system servicing. Maintaining aircraft fuel systems in acceptable condition to deliver clean fuel to the engines is a major safety factor in aviation. Personnel handling fuel or maintaining fuel systems should be properly trained and use best practices to ensure that the fuel or fuel system are not the cause of an incident or accident. Checking for fuel system contaminants. Continuous vigilance is required when checking aircraft fuel systems for contaminants. Daily draining of strainers and sumps is combined with periodic filter changes and inspections to ensure fuel is contaminant-free. Turbine-powered engines have highly refined fuel control systems through which flow hundreds of pounds of fuel per hour of operation. Sumping alone is not sufficient. Particles are suspended longer in jet fuel due to its viscosity. Engineers design a series of filters into the fuel system to trap foreign matter. Technicians must supplement these with cautious procedures and thorough visual inspections to accomplish the overall goal of delivering clean fuel to the engines. Keeping a fuel system clean begins with an awareness of the common types of contamination. Water is the most common. Solid particles, surfactants, and microorganisms are also common. However, contamination of fuel with another fuel not intended for use on a particular aircraft is possibly the worst type of contamination. Water. Water can be dissolved into fuel or entrained. Entrained water can be detected by a cloudy appearance to the fuel. Close examination is required. Air in the fuel tends to cause a similar cloudy condition, but is near the top of the tank. The cloudiness caused by water in the fuel tends to be more towards the bottom of the tank as the water slowly settles out. As previously discussed, water can enter a fuel system via condensation. The water vapor in the vapor space above the liquid fuel in a fuel tank condenses when the temperature changes. It normally sinks to the bottom of the fuel tank into the sump, where it can be drained off before flight. Figure 14 to 93. However, time is required for this to happen. Therefore, you should wait a period of time after fueling before checking the fuel sumps so the water and sediment can settle to the drain point. On some aircraft, a large amount of fuel needs to be drained before settled water reaches the drain valve. Awareness of this type of sump idiosyncrasy for a particular aircraft is important. The condition of the fuel and recent fueling practices need to be considered and are equally important. If the aircraft has been flown often and filled immediately after flight, there is little reason to suspect water contamination beyond what would be exposed during a routine sumping. An aircraft that has sat for a long period of time with partially full fuel tanks is a cause of concern. It is possible that water is introduced into the aircraft fuel load during refueling with fuel that already contains water. Any suspected contamination from refueling or the general handling of the aircraft should be investigated. A change in fuel supplier may be required if water continues to be an issue, despite efforts being made to keep the aircraft fuel tanks full and sumps drained on a regular basis. Fuel below freezing temperature may contain entrained water in ice form that may not settle into the sump until melted. Use of an anti-icing solution in turbine fuel tanks helps prevent filter blockage from water that condenses out of the fuel as ice during flight. The fuel anti-ice additive level should be monitored so that recommended quantity for the tank capacity is maintained. After repeated fueling, the level can be obscured. A field handheld test unit can be used to check the amount of anti-ice additive already in a fuel load. Figure 14 to 94. Strainers and filters are designed with upward flow exits to have water collect at the bottom of the fuel bowl to be drained off. This should not be overlooked. Entrained water in small quantities that makes it to the engine usually poses no problem. Large amounts of water can disrupt engine operation. Settled water in tanks can cause corrosion. This can be magnified by microorganisms that live in the fuel-water interface. High quantities of water in the fuel can also cause discrepancies in fuel quantity probe indications. Solid particle contaminants. Solid particles that do not dissolve in the fuel are common contaminants. Dirt, rust, dust, metal particles, and just about anything that can find its way into an open fuel tank is of concern. Filter elements are designed to trap these contaminants, and some fall into the sump to be drained off. Pieces of debris from the inside of the fuel system may also accumulate, such as broken-off sealant or pieces of filter elements, corrosion, etc. Preventing solid contaminant introduction into the fuel is critical. Whenever the fuel system is open, care must be taken to keep out foreign matter. Lines should be capped immediately. Fuel tank caps should not be left open for any longer than required to refuel the tanks. Clean the area adjacent to wherever the system is opened before it is opened. Coarse sediments are those visible to the naked eye. Should they pass beyond system filters, they can clog in fuel metering device orifices, sliding valves, and fuel nozzles. Fine sediments cannot actually be seen as individual particles. They may be detected as a haze in the fuel, or they may refract light when examining the fuel. Their presence in fuel controls and metering devices is indicated by dark, shellac-like marks on sliding surfaces. The maximum amount of solid particle contamination allowable is much less in turbine engine fuel systems than in reciprocating engine fuel systems. It is particularly important to regularly replace filter elements and investigate any unusual solid particles that collect therein. The discovery of significant metal particles in a filter could be a sign of a failing component upstream of the filter. A laboratory analysis is possible to determine the nature and possible source of solid contaminants. Surfactants. Surfactants are liquid chemical contaminants that naturally occur in fuels. They can also be introduced during the refining or handling processes. These surface-active agents usually appear as tan to dark brown liquid when they are present in large quantities. They may even have a soapy consistency. Surfactants in small quantities are unavoidable and pose little threat to fuel system functioning. Larger quantities of surfactants do pose problems. In particular, they reduce the surface tension between water and the fuel and tend to cause water and even small particles in the fuel to remain suspended rather than settling into the sumps. Surfactants also tend to collect in filter elements, making them less effective. Surfactants are usually in the fuel when it is introduced into the aircraft. Discovery of either excessive quantities of dirt and water making their way through the system, or a sudsea residue in filters and sumps may indicate their presence. The source of fuel should be investigated and avoided if found to contain a high level of these chemicals. As mentioned, slow settling rates of solids and water into sumps is a key indicator that surfactant levels are high in the fuel. Most quality fuel providers have clay filter elements on their fuel dispensing trucks and in their fixed storage and dispensing systems. These filters, if renewed at the proper intervals, remove most surfactants through adhesion. Surfactants discovered in the aircraft systems should be traced to the fuel supply source and the use and condition of these filters. Figure 1495. Microorganisms. The presence of microorganisms in turbine engine fuels is a critical problem. There are hundreds of varieties of these life forms that live in free water at the junction of the water and fuel in a fuel tank. They form a visible slime that is dark brown, gray, red, or black in color. This microbial growth can multiply rapidly and can cause interference with the proper functioning of filter elements and fuel quantity indicators. Moreover, the slimy water microbe layer in contact with the fuel tank surface provides a medium for electrolytic corrosion of the tank. Figure 14 to 96. Since the microbes live in free water and feed on fuel, the most powerful remedy for their presence is to keep water from accumulating in the fuel. Fuel 100% free of water is not practicable. By following best practices for sump draining and filter changes, combined with care of fuel stock tanks used to refuel aircraft, much of the potential for water to accumulate in the aircraft fuel tanks can be mitigated. The addition of biocides to the fuel when refueling also helps by killing organisms that are present. Foreign fuel contamination. Aircraft engines operate effectively only with the proper fuel. Contamination of an aircraft's fuel with fuel not intended for use in that particular aircraft can have disastrous consequences. It is the responsibility of all aviators to put forth effort continuously to ensure that only the fuel designed for the operation of the aircraft's engines is put into the fuel tanks. Each fuel tank receptacle or fuel cap area is clearly marked to indicate which fuel is required. Figure 14 to 97. If the wrong fuel is put into an aircraft, the situation must be rectified before flight. If discovered before the fuel pump is operated and an engine is started, drain all improperly filled tanks. Flush out the tanks and fuel lines with the correct fuel, and then refill the tanks with the proper fuel. However, if discovered after an engine has been started or attempted to be started, the procedure is more in-depth. The entire fuel system, including all fuel lines, components, metering devices, and tanks, must be drained and flushed. If the engines have been operated, a compression test should be accomplished, and the combustion chamber and pistons should be borescope inspected. Engine oil should be drained, and all screens and filters examined for any evidence of damage. Once reassembled, and the tanks have been filled with the correct fuel, a full engine run-up check should be performed before releasing the aircraft for flight. Contaminated fuel caused by the introduction of small quantities of the wrong type of fuel into an aircraft may not look any different when visually inspected, making a dangerous situation more dangerous. Any person recognizing that this error has occurred must ground the aircraft. The lives of the aircraft occupants are at stake. Detection of contaminants. Visual inspection of fuel should always reveal a clean, bright-looking liquid. Fuel should not be opaque, which could be a sign of contamination and demands further investigation. As mentioned, the technician must always be aware of the fuel's appearance, as well as when and from what sources refueling has taken place. Any suspicion of contamination must be investigated. In addition to the detection methods mentioned for each type of contamination above, various field and laboratory tests can be performed on aircraft fuel to expose contamination. A common field test for water contamination is performed by adding a dye that dissolves in water, but not fuel, to a test sample drawn from the fuel tank. The more water present in the fuel, the greater the dye disperses and colors the sample. Another common test kit commercially available contains a gray chemical powder that changes color to pink or purple when the contents of a fuel sample contains more than 30 parts per million ppm of water. A 15 ppm test is available for turbine engine fuel. Figure 14 to 98. These levels of water are considered generally unacceptable and not safe for operation of the aircraft. If levels are discovered above these amounts, time for the water to settle out of the fuel should be given, or the aircraft should be defueled and refueled with acceptable fuel. The presence and level of microorganisms in a fuel tank can also be measured with a field device. The test detects the metabolic activity of bacteria, yeast, and molds, including sulfate-reducing bacteria and other anaerobe microorganisms. This could be used to determine the amount of antimicrobial agent to be added to the fuel. The testing unit is shown in Figure 1499. Bug test kits test fuel specifically for bacteria and fungus. While other types of microorganisms may exist, this semi-quantitative test is quick and easy to perform. Treat a fuel sample with the product and match the color of the sample to the chart for an indication of the level of bacteria and fungus present. These are some of the most common types of microorganisms that grow in fuel. If growth levels of fungus and bacteria are acceptable, the fuel could be usable. Figure 14 to 100. Fuel trucks and fuel farms may make use of laser contaminant identification technology. All fuel exiting the storage tank going into the servicing hose is passed through the analyzer unit. Laser sensing technology determines the difference between water and solid particle contaminants. When an excessive level of either is detected, the unit automatically shuts off flow to the fueling nozzle. Thus, aircraft are fueled only with clean, dry fuel. When surfactant filters are combined with contaminant identification technology and microorganism detection, chances of delivering clean fuel to the aircraft engines are good. Figure 14.101. Before various test kits were developed for use in the field by non-scientific personnel, laboratories provided complete fuel composition analysis to aviators. These services are still available. A sample is sent in a sterilized container to the lab. It can be tested for numerous factors including water, microbial growth, flash point, specific gravity, cetane index, a measure of combustibility and burning characteristics, and more. Tests for microbes involve growing cultures of whatever organisms are present in the fuel. Figure 14.102. Fuel contamination control. A continuous effort must be put forth by all those in the aviation industry to ensure that each aircraft is fueled only with clean fuel of the correct type. Many contaminants, both soluble and insoluble, can contaminate an aircraft's fuel supply. They can be introduced with the fuel during fueling, or the contamination may occur after the fuel is on board. Contamination control begins long before the fuel gets pumped into an aircraft fuel tank. Many standard petroleum industry safeguards are in place. Fuel farm and delivery truck fuel handling practices are designed to control contamination. Various filters, testing, and treatments effectively keep fuel contaminant-free or remove various contaminants once discovered. However, the correct clean fuel for an aircraft should never be taken for granted. The condition of all storage tanks and fuel trucks should be monitored. All filter changes and treatments should occur regularly and on time. The fuel supplier should take pride in delivering clean, contaminant-free fuel to its customers. Onboard aircraft fuel systems must be maintained and serviced according to manufacturer's specifications. Samples from all drains should be taken and inspected on a regular basis. Filters should be changed at the specified intervals. The fuel load should be visually inspected and tested from time to time, or when there is a potential contamination issue. Particles discovered in filters should be identified and investigated if needed. Inspection of the fuel system during periodic inspections should be treated with highest concern. Most importantly, the choice of the correct fuel for an aircraft should never be in question. No one should ever put a fuel into an aircraft fuel tank unless absolutely certain it is the correct fuel for that aircraft and its engine as. Personnel involved in fuel handling should be properly trained. All potential contamination situations should be investigated and remedied. Fueling and defueling procedures. Maintenance technicians are often asked to fuel or defuel aircraft. Fueling procedure can vary from aircraft to aircraft. Tanks may need to be fueled in a prescribed sequence to prevent structural damage to the airframe. The proper procedure should be confirmed before fueling an unfamiliar aircraft. Fueling. Always fuel aircraft outside, not in a hangar where fuel vapors may accumulate and increase the risk and severity of an accident. Generally, there are two types of fueling process: over-the-wing refueling and pressure refueling. Over-the-wing refueling is accomplished by opening the fuel tank cap, on the upper surface of the wing or fuselage, if equipped with fuselage tanks. The fueling nozzle is carefully inserted into the fill opening, and fuel is pumped into the tank. This process is similar to the process used to refuel an automobile gas tank. When finished, the cap is secured, and subsequent tanks are opened and refilled until the aircraft has the desired fuel load on board. Pressure refueling occurs at the bottom, front, or rear of the fuel tank. A pressure refueling nozzle locks onto the fueling port at the aircraft fueling station. Fuel is pumped into the aircraft through this secured and sealed connection. Gauges are monitored to ascertain when the tanks are properly loaded. An automatic shutoff system may be part of the aircraft system. It closes the fueling valve when the tanks are full. Figure 14.103. Precautions should be used with either type of fueling. First and foremost, it is absolutely essential that the correct fuel be put in the aircraft. The type of fuel to be used is placarded near the fill port on over-the-wing systems and at the fueling station on pressure-refueled aircraft. If there is any question about which fuel to use, the pilot in command, other knowledgeable personnel, or the manufacturer's maintenance operations manual should be consulted before proceeding. An over-the-wing refueling nozzle for turbine engine fuel should be too large to fit into the fill opening on an aircraft utilizing gasoline. Clean the area adjacent to the fill port when refueling over the wing. Ensure the fuel nozzle is also clean. Aviation fuel nozzles are equipped with static bonding wires that must be attached to the aircraft before the fuel cap is opened. Figure 14.104. Open the cap only when ready to dispense the fuel. Insert the nozzle into the opening with care. The aircraft structure is much more delicate than the fuel nozzle, which could easily damage the aircraft. Do not insert the neck of the nozzle deeply enough to hit bottom. This could dent the tank or the aircraft skin if it is an integral tank. Exercise caution to avoid damage to the surface of the airframe by the heavy fuel hose. Lay the hose over your shoulder or use a refueling mat to protect the paint. Figure 14.105. When pressure refueling, the aircraft receptacle is part of a fueling valve assembly. When the fueling nozzle is properly connected and locked, a plunger unlocks the aircraft valve so fuel can be pumped through it. Normally, all tanks can be fueled from a single point. Valves in the aircraft fuel system are controlled at the fueling station to direct the fuel into the proper tank. Figure 14.106. Ensure that the pressure developed by the refueling pump is correct for the aircraft before pumping fuel. Although similar, pressure fueling panels and their operation are different on different aircraft. Refueling personnel should be guided through the correct use of each panel. Do not guess at how the panel and associated valves operate. When fueling from a fuel truck, precautions should be taken. If the truck is not in continuous service, all sumps should be drained before moving the truck, and the fuel should be visually inspected to be sure it is bright and clean. Turbine fuel should be allowed to settle for a few hours if the fuel truck tank has recently been filled or the truck has been jostled, such as when driven over a bumpy service road at the airport. Properly maneuver the fuel truck into position for refueling. The aircraft should be approached slowly. The truck should be parked parallel to the wings and in front of the fuselage if possible. Avoid backing toward the aircraft. Set the parking brake and chock the wheels. Connect a static bonding cable from the truck to the aircraft. This cable is typically stored on a reel mounted on the truck. There are other miscellaneous good practices that should be employed when refueling an aircraft. A ladder should be used if the refuel point is not accessible while standing on the ground. Climbing on an expensive aircraft to access the fueling ports is possible, but does not give the stability of a ladder and may not be appreciated by the aircraft owner. If it is necessary to walk on the wings of the aircraft, do so only in designated areas, which are safe. Filler nozzles should be treated as the important tools that they are. They should not be dropped or dragged across the apron. Most have attached dust caps that should be removed only for the actual fueling process and then immediately replaced. Nozzles should be cleaned to avoid contamination of the fuel. They should not leak and should be repaired at the earliest sign of leak or malfunction. Keep the fueling nozzle in constant contact with the filler neck spout when fueling. Never leave the nozzle in the fill spout unattended. When fueling is complete, always double-check the security of all fuel caps and ensure that bonding wires have been removed and stowed. Defueling. Removing the fuel contained in aircraft fuel tanks is sometimes required. This can occur for maintenance, inspection, or due to contamination. Occasionally, a change in flight plan may require defueling. Safety procedures for defueling are the same as those for fueling. Always defuel outside. Fire extinguishers should be on hand. Bonding cables should be attached to guard against static electricity buildup. Defueling should be performed by experienced personnel, and inexperienced personnel must be checked out before doing so without assistance. Remember that there may be a sequence in defueling an aircraft's fuel tanks, just as there is when fueling to avoid structural damage. Consult the manufacturer's maintenance operations manuals, if in doubt. Pressure-fueled aircraft normally defuel through the pressure fueling port. The aircraft's in-tank boost pumps can be used to pump the fuel out. The pump on a fuel truck can also be used to draw fuel out. These tanks can also be drained through the tank sump drains, but the large size of the tanks usually makes this impractical. Aircraft fueled over the wing are normally drained through the tank sump drains. Follow the manufacturer's procedure for defueling the aircraft. What to do with the fuel coming out of a tank depends on a few factors. First, if the tank is being drained due to fuel contamination or suspected contamination, it should not be mixed with any other fuel. It should be stored in a separate container from good fuel, treated if possible, or disposed of properly. Take measures to ensure that contaminated fuel is never placed on board an aircraft or mixed with good fuel. Second, the manufacturer may have requirements for good fuel that has been defueled from an aircraft, specifying whether it can be reused and the type of storage container in which it must be stored. Above all, fuel removed from an aircraft must not be mixed with any other type of fuel. Good fuel removed from an aircraft must be handled with all precautions used when handling any fuel. It must only be put into clean tanks, and efforts must be made to keep it clean. It may be put back in the aircraft or another aircraft if the manufacturer allows. Large aircraft can often transfer fuel from a tank, requiring maintenance to another tank to avoid the defueling process. Fire hazards. When fueling or defueling. Due to the combustible nature of avgas and turbine engine fuel, the potential for fire while fueling and defueling aircraft must be addressed. Always fuel and defuel outside, not in a hangar that serves as an enclosed area for vapors to build up to a combustible level. Clothing worn by refueling personnel should not promote static electricity buildup. Synthetics, such as nylon, should be avoided. Cotton has proved to be safe for fuel handling attire. As previously mentioned, the most controllable of the three ingredients required for fire is the source of ignition. It is absolutely necessary to prevent a source of ignition anywhere near the aircraft during fueling or refueling. Any open flame, such as a lit cigarette, must be extinguished. Operation of any electrical devices must be avoided. Radio and radar use is prohibited. It is important to note that fuel vapors proliferate well beyond the actual fuel tank opening, and a simple spark, even one caused by static electricity, could be enough for ignition. Any potential for sparks must be nullified. Spilled fuel poses an additional fire hazard. A thin layer of fuel vaporizes quickly. Small spills should be wiped up immediately. Larger spills can be flooded with water to dissipate the fuel and the potential for ignition. Do not sweep fuel that has spilled onto the ramp. Class B fire extinguishers need to be charged and accessible nearby during the fueling and defueling processes. Fueling personnel must know exactly where they are and how to use them. In case of an emergency, the fuel truck, if used, may need to be quickly driven away from the area. For this reason alone, it should be positioned correctly on the ramp relative to the aircraft.